Are doing get-ahead work for the EVA crew. There's also no bag for the crew to cut through when they arrive. We then demate again. Orion docks here, and now the arms aid during the EVAs, just as the RMS did during shuttle days and SSRMS does. Now, does it? SSRMS, do they ever stand on the end of SSRMS? Yeah. So afterward, the tug could then potentially be refueled, replenished with xenon to go either get another one or to do other things that are extensible for the human exploration system. Tugs are a good thing to have in your back pocket if you're a spacefaring nation. So these are things that we are doing presently to advance the technology in some of these key areas. We've got a refueling experiment up on space station right now that's involving advanced tools, and I have no time. But these, my only point here is these are all photographs of hardware, not CAD renderings of what we're going to do, but what we are doing now. And these are those other missions. Take a picture quick. Thank you.
Thanks, Ben.
All right, we keep proving how little time 10 minutes is. The next pair of speakers is Michael Esperman and Manny Leans from Boeing Company. Mike's the Director of Space Science and Advanced Space Utilization for Boeing. Manny is the Director of Autonomous Space Capabilities, and he will join in the presentation. They will address the inherent technical, schedule, and cost risks of the challenging mission and discuss how designing the asteroid redirect systems to incorporate existing high-heritage spacecraft systems and subsystems, leveraging proven performance, high reliability, and associated investments and experience will reduce overall mission risk, capitalizing on the extensive industry production and operations experience. So, Mike?
My name is Mike, as Jim said. This is Manny. We're from the Boeing Company. Today we're going to talk a little bit about maybe not so much the specific implementation of this mission, but ways to manage the risk that are inherent in just in a program of this magnitude. Which button is it, Jim, for chart?
Don't touch the bottom one. The full, yeah.
Okay, right. Figured it out. So really, it's going to be broken into two parts. I'm going to talk about similar concepts to what Adam talked about, and a little bit what Ben talked about, how we maybe can leverage existing capabilities that exist within industry and that NASA's already invested in to really help manage and mitigate the asteroid mission system risks. And then Manny's going to talk about specifically some investments that have been done both by us and by NASA in autonomous rendezvous and docking terrain relative navigation, how that can apply to the mission and also reduce the overall risk. So as everybody I'm sure recognizes and has been said several times today, it's a very ambitious program that NASA is trying to undertake. Lots of benefits to the nation and to humanity, and really trying to synergize the various things that are going on inside of NASA in terms of technology development, mission execution, science, et cetera. But there are a lot of, as everybody realizes, a lot of uncertainties on this particular mission, which really drive up the risk. It's already incorporating new technologies which have some inherent risks. We're going further away than we've gone in a long time in terms of distance from Earth. So the asteroid, they've talked about the uncertainty in its mass, and that drives system performance parameters. Launch date, launch vehicle, those are trades that are also uncertain. And then a real risk, I think, is the very ambitious schedule that has been proposed. Concurrent technology development at the same time that you're designing the mission and the mission systems. You've got to really be careful about what you're doing there. So really, I think mission success is going to depend on effective and very strong risk management. So my message here is that I think that the industry team, both industry, academia, and NASA, that NASA has to make a broader community involvement in this mission, I think will really go a long way towards minimizing that risk. There's an extensive amount of experience in industry from our current production programs on the commercial side as well as the existing NASA programs that can be used to mitigate risks. And I've listed really 5 key ones there that I'm going to talk a little bit more about as we go through the presentation. First of all, using flight-proven systems, high-heritage systems, will as your point of departure, definitely reduces the risk on the system. Utilizing a prime integrator, if you will, to integrate the solar electric propulsion technologies into the mission, I think also has a lot of merit. You can leverage the experience that the industry partners have to get that system integrated and working right. A lot of best practices to bring to bear. Launching on SLS really increases your margins. Increased margin increases your ability to handle unforeseen circumstances and reduces your risk. Ben mentioned designing the system for reuse. I think that's a really smart move. It maximizes the return on investment. No matter what you do, even trying to drive costs down and be affordable, this is going to be a very expensive investment for the country. So reusing that system only makes sense, and there's some things you can do early on when you do the design to enhance that reusability. And implementing an integrated GNC system into the autonomous rendezvous and docking portion, make it all resident in one vehicle. We think there's some real benefits to that, and Manny will probably touch on that, but in terms of testing, seamless seams, interface requirements, that types of thing, it seems like a smarter way to go. So the first topic, heritage systems reducing development and execution risk. There's a lot of spacecraft knowledge in America, in the industry. We've been, we produce spacecraft for, well, basically entire industries depend on the spacecraft that we produce. For example, XM radio, direct TV. So the reliability and mission success requirements on those types of platforms are, they're equally as important as they are for a mission of this magnitude as well. So you've got a lot of flight-proven design and qualification experience that are resident in the industry partners. Very established and repeatable processes and tools, and the personnel who know how to build these platforms. That's a real key benefit that could be brought to bear here on this program. Of integrated and well-exercised supply chain. Even though you're going to build just maybe one vehicle for this particular mission, if you need spare parts, you have to do some testing, something that you hadn't foreseen. If you can pull on that supply chain to get those parts or build up an engineering design unit in pretty quick time, that's a real benefit as well. Once again, 15-year lifetime for most of the commercial geocom platforms that are built out there, if not longer. Operational envelopes and limits, we know what the space vehicle is designed for, and we tested that, and we see it happen in operational experience. So we know how the vehicle is going to operate. Established launch vehicle and payload interfaces, up to 10,000 kilogram payloads can be accommodated on most of these platforms. I know Adam said that the Loral platform can go a little bit higher. So more mass is going to be, that gives you that margin that you're going to need to be successful. And as you're designing the mission, depending on the trades that, say, Ben alluded to, whether you do a two-piece spacecraft or a monolithic spacecraft, you can draw on the industry's either their systems, subsystems, or the entire platform for a turnkey solution. It gives flexibility to NASA. And really what that does, it allows NASA to focus on the hard things that need to be developed. The spacecraft's going to be, it'll be a tough engineering challenge, but getting those technologies done and getting them validated at TRL 6 and above in the time frame that we're talking about, that's a big job. And that way the NASA can focus on that. No, I didn't do that. I did not do that. I'm not going to update Firefox right now. Okay. Did I go? Okay. Okay, all right. So we'll go to the next chart. Integration experience for solar electric propulsion technologies. There are lots of use of SEP in today's geocom and other application space mission markets. The advanced solar electric propulsion that's been talked about for this mission is quite a leap in terms of power, both for the thrusters and for the solar arrays. But there's a lot of there's many years of operational experience out there operating these systems, doing station keeping at GEO, or in the context of the vehicle that Boeing has recently developed, the 702 SP. It actually uses the solar electric propulsion to orbit raise. Now, granted, it takes a little bit longer to get on station, but it really reduces your launch costs, which is a real benefit. Point is, there's a lot of experience on how to integrate SEP technology into systems out in industry that could be applied here for NASA. Lots of lessons learned from our experience in both production, design, and operations. Once again, solid supplier relationships with all the key producers. Some firms have indigenous solar array production test and build facilities and capabilities that could be brought. And state-of-the-art SEP test equipment also exists. Once again, the experience base is, for Boeing anyhow, it's well over 90 years of operational experience with SEP-powered vehicles. And there's the ability to do low thrust trajectory design mission planning and the navigation expertise with that is also becoming more important, and that can add to the mission success chances as well. SLS, what a great asset to have for this mission. NASA's building the SLS now. They're actually ahead of schedule in many instances. Vehicles on track to fly in the 2017, 2018 timeframe. That's really a fortuitous schedule coincidence. That if you can launch on SLS, basically you get more mass. You could possibly demonstrate a gravity tractor demonstration, a deflection demonstration if you have a massive enough spacecraft. You can launch on a direct injection trajectory to lunar gravity assist or straight to the target, depending on what the target is. It eliminates that spiral out phase and saves you about 2 years on the overall mission duration, or 1 to 3 years, depending on, once again, where you're going and how big it is. But the additional SEP technology maturation schedule that the SLS provides, I think, is a real benefit too. If we push back the notional launch date to when SLS is flying a Block 1 configuration, once again, that gives the technology folks a little bit extra time to get the SEP up to the right TRL. And a little bit of extra schedule margin is always good when you're running a development program. Designing for usability also maximizes the return of investment for NASA. After the asteroid retrieval mission is complete, there's probably still 5 to 10 years of remaining lifetime on the vehicle, if not more. You've got 50 kilowatts at beginning of life on station in translunar space now. What a great asset, once again, to have for any future exploration architecture pieces that come out there that either need a tug or just a power supply, or a lot of the other capabilities that the arm will have inherent in its design. You can also refuel it if you design that early on. That, once again, SLS can bring up quite a large quantity of propellant to translunar space to refuel it, or if it, during the operational mode, it can get back to Earth, you could refuel it even closer. But there's a lot of applications that you could have there. So thinking about it in terms of reuses should be one of the guiding principles in terms of the system engineering early on. And integrated autonomous rendezvous capabilities into the overall spacecraft simplifies the design and operations of the mission. The integrated system that has both AR&D and terrain relative navigation sensors on it, we feel is the lowest risk approach, and having those integrated into the flight system. It basically decouples the AR&D stuff, which is relatively mature, from the new technology propulsion development. Better integrates the GNC system performance overall, because you don't have 2 interfaces, you don't have 2 computers talking to each other. Streamlines the getting it ready to fly, simplifies the interfaces, and potentially you could use the sensors to do both the tracking far away and in close. And with that, I will turn that over to Manny and let him tell you a little bit more about that piece.
Okay, so quickly, we have the experience from the Orbital Express program back in 2007 of having flown optical navigation systems. There's a picture of what we flew back in back there six years ago on board the Astro spacecraft. Completed 6 autonomous rendezvous and docking scenarios. And one point here, which is not that commonly known, although we use the NASA AVGS system for corridor approach, actually all the acquisition and track was using optical navigation from hundreds of kilometers on all the way in to capture contemporaneously with the NASA system. So just wanted to get that out there to make sure everybody understands that. So fast forward to today, we have 2 different systems that, or one in particular that we are developing for flight, that being for commercial crew. We call that Vesta. That is allowing us to do completely autonomous rendezvous and docking. We see really good applicability of a similar system for asteroid and planetary type missions as well. So kind of put together sort of a notional ConOps here, and I don't have time to brief this in detail, but probably one of the important takeaways here is that so first of all, a lot of similarity in our thinking in terms, from what John Brophy was saying earlier, in terms of visible sensors and Lidar type sensors. definitely having something that gives you long-range track, really good precision vision and feature identification in sunlight is excellent, and the Lidar sensor to give you range and 3D shape, very important. The thing we'd like to add into the mix there is long-wave infrared. I think we were among the first, if not the first, to fly an LWIR sensor on Orbital Express, and since then, lots of folks are using them for autonomous rendezvous. We'd like to throw that in here as a suggestion for this mission, ARM, as well. The thing that brings to you is really good solar immunity, sun immunity, and ability to see into dark shadows. So it helps with shape determination. So if you look through this, using visible sensors to acquire at long range, and then stepping on in, and then using these disparate sensors, fusing the data to do the asteroid characterization tasks, and then to support the capture, the D-spin, and then also the capability of dual use on these sensors for inertial nav versus relative nav. And just a quick one on the benefits. I think I said some of this as to why a long range or long wave infrared camera is good. And I think, gosh, I finished. Wait, I feel like it's something else I should have said. All right. We have time for a question.
But thank you. And again, we don't have time for questions, so we'll catch them at the end. Thank you.
All right, we're cooking right along here. Our next speaker is John Ringelberg. He's a senior staff engineer at Lockheed Martin, Denver, working in the Civil Space Advanced Programs Group. He's the principal investigator for an IRAD effort advancing autonomous rendezvous, proximity operations, docking, and landing technologies. His presentation will provide an overview of integrated sensing systems from previous missions with direct correlation to ARM. Particular technologies for asteroid relative nav and characterization will be highlighted, and a brief summary of solar electric propulsion heritage and technology will also be provided. Thanks, John.
Thanks. Continuing on that theme, kind of the last few presentations of trying to leverage some of the work that's been done on either previous programs or on current programs, ongoing programs. One obvious example is Osiris-Rex, which is a mission Lockheed has a strong role in, but Goddard leading this. There's a lot of things that are being done on Osiris-Rex that probably are very applicable to what's going to happen for what you need to do for the asteroid redirect mission. There's particular areas that it's a much bigger asteroid that Osiris-Rex is going to. They're going to have a lot more time, most likely station keeping, mapping and characterizing the asteroid, but there's still a lot of the capabilities, particularly that are going into Osiris-Rex, that you can extend and apply to the asteroid redirect mission. Both optical and what was mentioned earlier, Lidar usage for Osiris-Rex and mapping. There's some areas, particularly for the optical navigation, that we're doing some work that can improve the resolution or the accuracy for your targeting for what Osiris-Rex does, which is the approach and sample capture, contact and sample capture. That's extensible, whether it's the bag capture or more of a robotic capture, a close-in approach such as that Ben talked about. Another mission further in the past, but similar type operations. Wanted to mention the XSS-11 mission, which most of you probably are familiar with, maybe not everybody, but this mission was a AFRL mission, very successful, didn't do capture or contact, but did a lot of proximity operations with different non-cooperative targets. And that's one of the key things that I wanted to point out here was what the asteroid redirect mission is going to do. There's a need for being able to go up something you know almost nothing about. You don't know the surface features, you don't know its spin rates, you don't know how it's moving. So missions like this, lessons learned from that and work since that can be used to apply for going up to a non-cooperative target, performing proximity operations, characterizing it. And the other part of it is the safe operations in proximity to your target, making sure there was a lot of work done on this that was good bit of it autonomous, where it had to plan your maneuvers ahead of time on what your natural motion and force motion, well, for the asteroid mission, force motion circumnav around your target, how you're going to do that safely, how you plan ahead, and this being so far out, using things you've done in the past to be able to build on those and do your safe operations in close proximity to a target that's so far away that you may not have the continuous communication with. Another area that we've been working on, kind of extensible to this, doing different IRAD and CRAD work we've done is particularly with the optical nav. That was mentioned earlier as one of the key features that's needed for approaching the asteroid, whatever the ARM target is. We've done a lot of work in this area. There's also a lot of other people doing work in this area, but we're kind of advancing. This is something that's probably going to help out Osiris-Rex to some extent as far as the precision approach capability, but using natural feature tracking to map the surface and to plan out your approach for the capture. Another area, our coherent technologies area, spends a lot of work on the laser or Lidar type mapping and characterization. Two different methods we mentioned in an RFI response that can be combined particularly used for characterizing the asteroid so you understand it for the approach and capture part of it. Digital holographic imaging gives you some work we've done. We've tested out. Our coherent group does a lot of work on the terrestrial, but also applying that to space applications. Using that's going to be important to characterize the asteroid as you approach it and to understand what its motions are before you capture it. Another area is the polarimetric sensing, hard word to say, for asteroid composition mass. You're going to need to understand the surface before you go up and grab it. You're going to want to understand that anyway, depending on what your capture and grab hold of technique is, whether that's robotic. Particularly if it's robotic, you're going to want to understand that surface to the greatest extent possible before you try and grab hold of it. And then I also wanted to mention here, some of you familiar with, there's a facility we have in Denver called our Space Operations Simulation Center. This is a large facility, and that's not a real asteroid inside the SOSC, but it's a picture we stuck in there to give a kind of an idea of how big the facility is, and that if you wanted to and you felt the need to, if it helps the mission, you could put an asteroid mounted inside there. That's a 7-meter correlated to the size of the SOSC. But that's going to be a key part, I think, of this mission, kind of reducing the risk of some of the technologies that make this a difficult mission. How can you want to ground test them in the best environment possible or most realistic flight-like environment as possible. So using facilities like SOSC to test out those technologies for the robotic mission to the asteroid approach and capture I think is key. One thing in our RFI response, we covered the sensing systems primarily, and I wanted to focus on that during the few minutes here. But also, we discussed SEP a little bit at Brian Dempsey, a guy at Lockheed Martin, did our input for that RFI response. And really, we kind of covered what's already been covered at some of the other presentations here, the 4 key areas that need to be addressed to enable the SEP for this mission. Thrusters, the Hall current thrusters, seems to be the focus for everyone here. That's provide good high power to thrust to power ratio. Another point out is the power processing units are a very mature technology for Hall thrusters. Another area is solar arrays that was mentioned several times. A lot of heritage and experience in industry that can support what's needed to be done for the ARM mission. A lot of experience with that, whether it's space station or all the missions you see listed there. And then the same thing with going to xenon tanks. We discussed a little bit in our response. There is a trade whether you want to do a single large tank versus multiple small tanks. There's advantages and disadvantages to each. Some single large tank be a less complex system, but there's the smaller tanks probably have more applicability to other missions. So there's more extensibility to other spacecraft. Continuing with the SCP, this is the last chart actually. One of the key things also going to be for the electric propulsion system is the integration and validation of the entire system. Mentioned here, there is, I think the last presentation mentioned a lot, there's a lot of experience actually, more than you would expect in SCP areas. The AEHF mission was a good demonstration of how you would use solar electric propulsion to raise an orbit of a vehicle. And then some other areas, there's been plenty of flight experience with a 4.5 kilowatt Hall thruster systems, getting larger into the thruster systems. And then we've actually done some work developing even bigger thruster systems up to 13 kilowatts. So did I catch us up there?
That was great.
And that's it. Thanks.
All right, so we're gonna take a question if we got one. Wake up. Anything from our virtual audience?
Quite a few questions coming up. All right, we've had quite a few questions coming from virtually from our listeners. I'm trying to see if there's one from a recent one. There was a lot of discussion about using electromagnetism. But that's probably a longer discussion because there's been 3 or 4 things come in about that. So here was a question on a recent one about robotic capture being vulnerable to surface dust and or shorting the SEP thrusters, and that came in after the Goddard presentation. Do you want to address that one, Ben?
The question was about dust in the robot?
And the SEP thrusters.
Well, hopefully the dust doesn't get all around to the SEP thrusters. But back in Constellation days, we built a chamber at Goddard to specifically either rain down dust or simulated regolith on mechanisms or have it hop up from below with the shaking tray. So we have the ability at Goddard not only to do particle redistribution analysis, which we honed for Hubble Space Telescope, EVA operations where we were very contamination sensitive, but specifically for the work that was going to be done with stuff driving around and walking around on the moon, we had this chamber available. So yes, that is a real issue. Whoever sent that in is a very observant questioner, and we've got facilities in place that could help buy down that risk.
Also, we've demonstrated on Mars the ability to detect our magnetism.
Yeah, good point, good point. A lot of operational experience on Mars from our friends who are up there now, driving around. Yeah, good point, Brian.
We'll hold. Do you have something that's pressing? Otherwise, I'd like to go to the next presentation, but we'll get back to a lot of the questions as we go on. Our next presenter is virtual. Jonathan Roble from Honeybee Robotics. Jonathan works there in the Robotic Spacecraft Mechanisms Corporation in Longmont, Colorado. Honeybee develops technology and products for next-gen advanced robotic and spacecraft missions for NASA, DoD, academia, and industry. Jonathan will discuss several enabling component technologies for asteroid rendezvous, proximity operations, characterization and capture, as well as technologies that can enable retrieval of a portion of an asteroid from the surface. Jonathan, are you out there?
Yeah, I'm here.
Hi, go ahead.
Can you guys hear me all right?
Yes, we can hear you great. Thank you.
That's great. Thank you. Thanks for the introduction, and I appreciate the opportunity to present at the synthesis workshop. Like you said, I'd like to just cover some of Honeybee's technologies that can contribute to asteroid redirection systems. For background, just like to say Honeybee Robotics is founded in 1983, has been developing spacecraft mechanisms and systems for 30 years. We consider our participation in NASA missions a key aspect of our business and take pride in the performance of our contributions, including the 2003 Mars Exploration Rover, rock abrasion tools, the 2011 Mars Science Laboratory robotics sample manipulation system and dust removal tool end effector, Phoenix Mars Lander, TEGA, dust cover and icy soil acquisition device. Honeybee Robotics has done successfully 300 plus excavation on Mars, and we have 3 gadgets there now. As you can see, Honeybee Robotics has technologies suitable for topics 2, 3, 4, 5, and 6 of NASA's Asteroid initiative. But currently I'd like to talk to topic 2, the asteroid redirection systems. And our sensing technologies for rendezvous, prox ops, characterization, and capture. We have some technologies we think that really help you see the asteroid. One of them is our laser-induced breakdown spectroscopy, and that's LIBS. It's currently implemented in our terrestrial applications. It allows us to vaporize and ionize surface material, so you create a puff of plasma at the surface. We're then able to capture the emission spectrum as the plasma cools and recombines. The emission spectra is representative of the surface material without any contaminants from physical interaction. And so we're thereby attaining surface material composition without ever physically touching the surface. As some of the presenters mentioned before, you're coming upon the asteroid possibly with very little information about its composition, materials, and bulk structure. And we think this is an excellent way of helping reduce that uncertainty before physical interaction with the asteroid. This is pretty similar to the MSL ChemCam, and this is a pertinent precedent for performing this type of observation. However, we are proposing to do it at a standoff distance so that you don't have to be quite as close to the material, surface material. The other technology is 3D Lidar. It's an improvement to machine vision that assists with detail-oriented operations while maintaining global awareness. It's operating much in the way that the human eye does. So there's a central area of high resolution for detail work combined with the larger area of low resolution for context and motion tracking. This is achieved by being able to produce a higher res laser pattern on an area of interest while doing a sparser laser pattern on the global area. You're thereby able to detect dynamic changes in the field of view and focus that laser scan pattern on an area of interest while maintaining like a global awareness. It allows us to map and track the surface of the asteroid, and this is, again, significantly important for conducting proximity operations around an uncharacterized object, something that might have sizable relief, especially where you're looking to land a spacecraft and do anchoring operations that could be looking for a very specific placement. So both of these technologies allow a spacecraft to characterize its otherwise unknown target and operate inside of a feedback loop and control algorithms for proximity ops. Now, in addition to these technologies, to further characterize the asteroid before interaction, we have done past work with impactors, which would, in addition to giving you composition, it could give you bulk property information by characterizing the ejected plume from impact. This is our cross technology. In addition, we can touch it with a touch-and-go sampler that allows you to use a tethered sample collection to assay the surface before committing to it. And this here is basically a propelled drill. Furthermore, we can harpoon sample it, and these will be talked about in other discussions, which can again give you that a priori knowledge before touching down. We can drill with Honeybee's extensive history in robotic drilling and sample collection. We can get below just the surface properties of the asteroid to understand how it's going to interact when you attempt to apply redirect forces to it and touch down on it. Once you're down there, we can inhale it, as we say, with a pneumatic sampler and excavation system that allows us to collect either cutting tailings or loose surface materials. And we can snare small objects using our lasso technology. And then we can also anchor to it with self-opposed multi-mode anchoring technologies that we have developed through past work that will allow you to touch down and produce a firm base station with it. Lastly, we have done work with full asteroid capture if it's small enough. And these are just some of the capabilities that we have, and others will be talked about more in the different topics. We think that the past work that Honeybee has done has prepared us to support an asteroid redirect mission. And if you guys have any questions, I guess I'll stick around afterwards or open them now if there's time.
Okay, great, Jonathan. I think we have time for one or two questions, preferably first of all focused on something directly for Jonathan, either here or is there anything virtual? Okay, well, Jonathan.
And if not, I encourage you guys to contact us at info@honeybeerobotics.com with any follow-up information requests.
Okay, thank you.
You're welcome.
And if you can, we would appreciate if you can stick around for our discussion later on.
Okay, our next speaker, Stephen Warwick from Northrop Grumman. He's a system engineer in the System Engineering Directorate. He earned his bachelor's degree in physics from Leicester University in the United Kingdom and his master's at Cranfield University. Steve will talk about an integrated sensor system to support asteroid characterization, proximity operations, and capture.
Thank you very much. It's a pleasure to be here this afternoon. I'm here on behalf of Northrop Grumman, and I'm going to be talking about the integrated sensor system. What we hope to do with this was look at a layered approach that will give us information as we approach the asteroid. And one of these buttons works. Top one?
The top one's a laser, so watch that one.
Yep.
Then,
there we go.
left and right.
All right, this is part of 3 talks that Northrop Grumman will be giving over the next 2 days, provided people in Washington have any sense. Today I'm talking about integrated sensing systems. Tomorrow we're looking at the asteroid deflection system that's given by Jim Munger. That's pushing the larger objects. And then also tomorrow afternoon we're looking at asteroid capture with Howard Eller. So what we were hoping to do when we took a look at this is produce a layered sensing approach that is going to buy down risk as we fly towards the asteroid. This is going to be something unusual in NASA land because we are not going to know what we're really going to do until we get close to the object. We're going to be launching with a significant amount of risk in the program. And when we were looking at what sensors were useful to us and what would help us buy down the risk, we had a straw man mission. We gave an orbit condition code of 1. If you know these things, that's actually knowing the orbit very well. H-mag of 28.5, that's the brightness of the object from the ground. But what we don't know about the object at all is the real diameter, the mass, the spin rate, whether there's a binary with the object or any kind of debris field. And what this series of sensors is going to do is find that information out and reduce the risk to the capture vehicle. All right, so starting 10,000 kilometers or more away from the asteroid, we suggested visible and near-infrared band telescopes, maybe 6-inch optics, and they have quite a large field of view, and we'll be scanning those to look for the asteroid. One of the things about approaching one of these asteroids is even when the orbit condition is relatively good, we're still not 100% sure where they are. The mission is going to have to find the asteroid as it approaches. And the goal here is to improve the orbit accuracy, know our distance to the object as well. With some of the other information we may be able to find out. We may be able to get spin state from a light curve as well using this instrument. But primarily, this is about finding the asteroid. And there on the slide on the right, you can see the advantage of infrared over visible. It gives you a better idea of the size of the object you're going to be looking at. Okay, we get closer to the object. From 100 kilometers or so, we're suggesting a radar, ground-penetrating radar. Obviously, that gives you characterization of the shape of the object. It improves your ranging to the object. Now you know, even to higher accuracy, where the object is. You're going to get some information about the spin state or the tumbling nature of the asteroid. And of course, because it's ground-penetrating radar, that's going to give you your first indication of whether you're dealing with a monolithic rock or you're dealing with one of these rubble piles. And that's obviously going to be critical for the safety of the capture spacecraft as it approaches the object. Getting closer still, 50 kilometers or so, Lidar, be able to generate a 3D model of the asteroid as it spins. And obviously, we don't expect these objects to be circular. They're going to be quite irregular. This will give us our indication of what nature of irregular object we're going to be looking at. Getting closer still, we quite like this one. This is a CubeSat. Back in 2010, Northrop launched a CubeSat called Mayflower. The next generation of that, Plymouth, is a 3-axis stabilized 3x1 CubeSat. And it also has some delta V on board, 20-25 meters a second. It has capacity for a reasonable amount of solar array on there as well. And it has its own instrument suite called DARC that has a camera, radar, and LiDAR of its own. And what you get from that is the ability for the capture spacecraft to be sat a reasonable distance away from the asteroid, safe from any debris or any other problem that the asteroid may threaten the capture vehicle with, and get very, very close with one of these objects, with one of these CubeSats, down to 50 meters or so range. A real advantage of this is we realize that as you approach the asteroid and station keep with the asteroid using the CubeSat, and you watch it for a couple of days, then relative to the primary spacecraft, you're going to see very slow acceleration, and that's the gravitational field of the asteroid. And that will give you your first indications of the true mass of the asteroid that you're going to try and capture. And getting closer still, and this is another CubeSat concept. If the ball there looks familiar, that's because we developed it with Honeybee for a discovery program in 2010, and also an Ames Research Center. We call these impactors, really, we've also used the name thumpers. They're intended to impact very slowly, meters a second. The accelerometers inside the ball give you more information on the composition of the asteroid, whether you're hitting dust, grains, or solid rock. And then there's another version, the 1U CubeSat, that's got cameras on board and an electrostatic probe to give you any idea of any kind of electrical field that the asteroid may have in any kind of dust environment around it. Both the CubeSat concepts we've shown here, they are moderately low TRL as it stands at the moment. But we've shown that you can go from concept to launch with a CubeSat in 6 months or so. So we would expect, if we were going to do something like this, to actually be flying the CubeSats ahead of time in low Earth orbit. But in both cases, they're not exquisite technology. They are commercial off-the-shelf type technology, and we achieve redundancy by having multiple copies of all the CubeSats we've shown here. So in summary, hopefully what we're showing here is a layered approach that's going to buy down the risk as we actually fly the mission. How we get close to the object, how we find out what the object really is, and how we can model the composition, the shape, the tumble, and spin of the object on the ground in such a way that safe capture of the asteroid can be achieved. All right. Thank you very much.
All right, we have time for questions. Yep.
Can you give us an idea of what a ground-penetrating radar might cost?
I'm afraid I can't. No, I don't have that information.
Anybody else? Anything coming in from our tweet or website?
Nope.
Okay.
Thank you.
Thank you. Our next presenter is Richard Disley from Ball. Rich works in business development in civil space and technologies at Ball Aerospace. He is primarily responsible for the pursuit and formulation of instruments and spacecraft for science missions. He received a doctorate in planetary sciences from Caltech in 1994. His talk will evaluate sensing requirements for ARM and present candidate systems to meet those requirements, and he escaped a flood, I believe.
Along with several other folks in the room, I think. So,
Yeah,
it's getting better now, though, at least in a lot of areas. So this is sound kind of familiar to it's kind of along the same theme of several other talks. So I'm gonna focus more on a couple of things toward the end. But we looked at the nominal arm scenario to say what are the what's the minimum base set of sensors that you might need for this. And just to get to the punchline, I see a minimum set being a narrow and wide field of view visible imagers and an imaging LiDAR. Sounds like a similar conclusion, although there's some nuances there. What sensors are available? I want to talk to that a little bit. Are there some gaps in the sensing technology? We've heard a lot about there are a lot of high TRL things available right now. I think that's true in the hardware side. I'm more concerned about the fully autonomous software for prox ops. There's a lot of work going on there, fantastic work in a lot of different locations, but you got to piece all that together and make it robust and fully autonomous for flight ops there. That to me is a big kicker that we need to concentrate on. This is also, as we've heard, applicable to a number of other mission concepts, recon missions to small bodies, AR&D, orbital debris remediation, satellite servicing. So I'll leave it at that. So this is my rendition of what the mission looks like. Several different distances here and what kind of sensors you can see here being needed to be applied for navigation and prox ops. The narrow field of view imager far out. As you get in closer and closer, you start bringing in LiDAR in order to get bearing information, then pose information further in. Need to get surface features and have those surface features blended into the pose model as well. But what's missing out of all these that I see is that you don't really have any kind of information, solid information anyway, about mechanical properties of the target. Now I've heard a lot of good talk, and I want to hear more discussion about this airbag technique being robust to any range of mechanical properties. That would scare me, thinking about this is going to be a tens of minute kind of operation to go in and move in, maneuver around something like that, encapsulate it, and then have some other diaphragm come around it, and then release the airbags. In the meantime, nothing has touched the surface at all. I think there might be a range of different con-ops we might think about here, depending on whether we've got good information about the mechanical properties or not of this object. So I would think you would want to be informed of that ahead of time, not just infer that. So getting back, though, to flash LiDAR, there are a number of different candidate technologies out there that are high TRL right now. We have one at Ball as well. This VNS, the Vision Navigation Sensor, flew on STS-134. Here you can see a visible image along with there's a visible camera along with that. The VNS flash LiDAR intensity image is here, and the range image is here as it's approaching this docking ring on the ISS. And flash LiDAR, as you may know, illuminates an entire field of view all at once. All the pixels come back with a range in real time. This particular device operates at 30 hertz. You can enhance this with adaptive beam steering. We've done some of that at Ball. Of this unit didn't have that, but there are ways to enhance the operability of this for high dynamic range targets. And we've also looked at ways to enhance the radiometric performance. You can make this compatible with low albedo targets by some pretty simple tweaks to this. This was made to look at retroreflectors on the ISS, but you can see, seeing a lot of the skin of the ISS where the retroreflectors aren't. There's a retro right there, that very bright object. But you can tweak this by removing the optical parametric oscillator, for instance, get about 5 times the performance on that. There are a number of different things you can do to, if you're willing to compromise eye safety, you can make this be able to see a lot on a dark target. As I mentioned, the technology gap I see is the need for robust, real-time, fully autonomous proximity ops. This has been looked at from a number of different angles. We've heard about the SOSC. As I understand, there's going to be a Morpheus landing test that looks at terrain relative nav and hazard avoidance in the loop as part of that. Those are all great things. They move us the right direction. One example of data here is to fuse visible data from the camera with the Lidar image and be able to get information real time, and that doesn't matter what the illumination conditions are. So that needs to be. You need to know exactly what features you're seeing on the target as well. So you get the full pose estimation in real time. So you know where you are relative to all those features on the asteroid as you're doing these proximity operations. As I've mentioned, I don't see this as being done in pieces right now. There needs to be a full end-to-end simulation that brings all this together, I think, to really make this robust. I think that's going to be a major hurdle in this mission. As you saw in John Brophy's talk as well, there was this picture was up in the upper right-hand corner of a possible augmentation to some of the sensors that might be on this. This was, not really a CubeSat, a sphere-sat, I guess. You saw on the last one there was a sphere as well. This is actually pretty high TRL now. We've developed this. We've done testing over the past 4 or 5 years at Ball, and we have this up around TRL 5 right now as a potential payload for small body missions. And this is just one scenario that might play out down at the bottom here, where you have a spacecraft in close proximity to a small body, asteroid in this case, deploying it out the back end, letting it free fall down. You don't have to make this very shock tolerant. In a low G situation, it's like dropping your pencil from about a meter off the ground here. It'll bounce around the surface, eventually settle down. In this particular scenario, we were using this to try to measure the inherent strength of the object, not just from the coefficient of restitution from hitting the surface. It does have accelerometers as a package on this, but also by having a small explosive charge on it to make a cratering experiment. The size of the crater is a direct function of what the strength of the material is. The deep impact experiment showed that as well. That was one of the premises of it anyway. So what the size of the crater here will inform you a lot about the strength of the material. Is it competent rock or is it a rubble pile? But note that there are limitations to this. You're not going to drop this and have one of these spheres be captured in a system unless the object is of 100 meters or so or larger. It's just not going to be a large enough gravitational well for it to be captured. So this is more of a scenario for maybe the go grab a rock scenario rather than going grabbing the entire asteroid. Also, for concepts of, it'd be nice to have a small free flyer, something that includes maybe a contact probe, like a little hummingbird to have a proboscis to go and do touch and go surface measurements on the surface. It'll also provide a very unique vantage point for imaging the capture sequence. I think, for public outreach of this, it'd be really nice to have a secondary spacecraft watching the entire process happen. So in conclusion, the arm sensing requirements we see being needed for capture are 1, range, 2, pose estimation for a resolved target, and 3, high-resolution visible imaging that's actually correlated to that pose estimation. Those measurements need to be made autonomously in real time. There are mature sensors for making these measurements, but the software is where the development needs to be. And separate flight elements to contact or perturb the target surface, I think, can reduce mission risk. Thanks.
Thank you. We have time for a question for Rich, if in the room or virtually. Go ahead. Go to a mic, though, please.
I can say it really loud. How much do those surface probes, the mass estimates for those?
Well, the question, if you could.
Yeah, what was the mass estimate for the surface probes? It can vary quite a bit, but the kind of the minimum mass that we see as being viable is on the order of 5-6 kilos. The instantiation you saw there had a couple of kilos of actual high explosive on them in addition to that. So they were in more like the 10 kilo range.
Any others? Okay, thank you.
There was a suggestion.
What was the suggestion?
The suggestion was to put an array of different sensors and devices up and relay the coordinates and information back to the capture vehicle.
An array of sensors. Well, actually, what we were thinking about was an array of sensors. Some of them have geophones on them. Some of them have explosive charges. You can make a crude seismic network that way. It's hard to emplace these with any control, so you have to be willing to have that uncertainty in that sensor net. But that is a good thought.
Okay, thanks, Rich. Our next speaker is Mark Haynes from the Jet Propulsion Laboratory. Mark received his PhD in applied physics from the University of Michigan in 2012. He joined JPL in June of this year, and his background is radar, microwave scattering and inverse scattering, and medical imaging. In this presentation, he'll give an overview of possible applications of radar as an asteroid characterization and avionics tool.
All right. Good afternoon. Thank you for having me. Like you said, I'm going to be talking about a couple ways in which radar could aid future asteroid missions. It's a pretty general talk. There's a lot of overlap with some of the other things, but hopefully it'll generate some more detailed discussion later. So the applications I'm going to talk about are aimed at addressing the following points of the RFI, mostly characterization and some avionics. In general, these systems are envisioned as integrated sensing systems to be used as an avionics tool with the possibility of secondary science. So real quick, just some features of radar. It's self-illuminating. It works in the shadow. It can see through dust. It's very fast. It works at a near far range. And the echoes contain sort of three pieces of information: how far away you are, relative motion in the form of Doppler, and then also lots of information on the physical scattering of the body. So just to give it some context of where radar has been used in the past, most everyone's familiar with the Goldstone and Arecibo asteroid radio tomography. In terms of planetary missions, Cassini and Magellan had radars that shared the communications dish. There have been 3 sounding missions, 2 to Mars, MRO and Mars Express, and then the Rosetta Concert radar heading to the comet. All the Mars rovers have gotten where they needed to go with the help of a landing radar, and the Apollo and Shuttle used rendezvous radars, and to this we can add all the Earth science remote sensing systems. However, for all the asteroid missions to date, there have been no in-situ radars. So those these are primarily science missions, and so some of the aspects of ARM and other parts of the initiative are a little more pragmatic, and so a few other utilities of radar can come out and contribute. So the first is radar sounding, with the simple purpose of mapping the regolith. So this is to get the internal structure, the bulk dielectric properties, and so by extension, the density distribution, where to anchor redirect thrusters, where to pick up samples or possibly boulders, and of course help improve trajectory estimations. So radar is the only active modality capable of subsurface imaging. And there are 2 ways you can think about doing this. What I would call scanline projection, so this is like ground penetrating radar, and the other is dielectric inversion. So in the first case, it's relatively fast. It gives you basic anatomy of what you're looking at, boundaries, edges. This is similar to the way the Marcis and Sherrod Mars polar images were processed. The second is dielectric inversion. So for this, you voxelize the body you're interested in. You have an electromagnetic scattering model, an iterative dielectric estimation technique, and you solve the inverse problem. So this is a little closer to the way Rosetta Concert is going to be working. And the advantage of this is it gives you the actual physical properties of the body of interest. The depth of penetration and the resolution trade off with frequency, but generally you need a pretty low frequency radar to do sounding. So we're talking hundreds of megahertz or even lower. Okay, so the next application is tomography, and you can think of this as an in situ Goldstone analog. So asteroid tomography is pretty well understood. The echoes that come back contain range information as well as Doppler in terms of what part of the asteroid is spinning towards you or away. They come back in a series of delayed Doppler images. These go into a shape reconstruction algorithm, and out pop the size, the shape, the spin axis, your range of target, and the relative motion. So anything you can think to do with that information, you can get it from radar tomography. The frequencies are generally a little bit higher. This is for resolution, and you don't want it to penetrate too deeply. And it only requires coarse antenna pointing because all the information is contained in the echoes. So there are a lot of computing technologies for tomography. Some things that are unique maybe to radar. The first is using the Doppler in sort of differential mode, so to reassess rates of change of spin due to deflection or what have you. And the second, this one's kind of new. It's to use delayed Doppler images as a form of GPS proxy. So if you wanted to give the spacecraft a better idea of where it was, you turn the radar on the body, you take a couple echoes, and you go to a table lookup, and you say, okay, now here I am relative to the body. And the advantage is this is a direct measurement and relatively fast. So this is the grab bag slide. This has some other, some overlap with some other sessions. So if there are going to be multiple crafts moving around, rendezvous radar is something to use. I think the idea would be to try to integrate it, maybe with a sounding radar to save on hardware. If you have a radar, you can always use it for altimetry and landing. The caveat, of course, in microgravity with low velocities is that laser rangefinders do just fine. But you can always use this as a backup. These two applications are sort of deflection rather than redirection. So you have two spacecraft, one orbiting the body, another one that's going to hit it. You can use the delay Doppler and get a better sense of how it's now spinning or how it's now moving. The advantage is it could look through the ejecta and it could maybe even track the ejecta. And finally, so this is a little different, a little new. This is a case of a single spacecraft-based redeflection, impact-based redeflection. So let's say you're 3 to 4 days out from the body. You turn the comm antenna on the asteroid. You do the tomography problem, give the craft an idea of where and when exactly it's going to hit. It's basically a targeting problem. Okay, in terms of the system configurations, to do tomography and sounding, you actually only need one antenna, which is kind of nice. For sounding, though, it needs its own separate low-frequency antenna. If you double up on the communication dish, you'll be at the higher frequencies, probably of the DSN, and so you're limited to some of those applications. In terms of power, what you need to run these systems, it just goes with range. To give you some examples, Earth-observing radars typically operate in 1 kilowatt peak power range. Airborne systems, 10 watts. And if you're really close, for whatever reason, you could use your cell phone. And so scanline sounding, altimetry, targeting, and some tomography are candidates for onboard processing. Dielectric conversion and more sophisticated tomography are probably going to have to be sent back. And I'll just wrap this up by saying that electromagnetic scattering models, antenna models, and radar system models have gotten to the point where we can actually simulate these systems end-to-end before turning a screw. And so we can tweak the frequencies, really assess whether or not they're going to work at a relatively low cost. So that's it. Again, these applications were mostly characterization and avionics based. And that's it. Thank you.
Okay, we've got time for questions. Don't see any online, although we are delayed a little bit. Yep, we got one.
Is there any advantage of having a lot of power? You said a kilowatt from Earth orbiting systems, but we're going to have a spacecraft that might have a lot of power. Will that provide you any advantages?
Oh, yeah. SNR, it will always help. And then you can just do these, you can have much higher orbits. You can do the same work much further away. It's pretty much what it gets you.
All right, thank you. All right, let's see. We got to check. We had intended the next presenter to be MDA, Paul Fulford. Okay, great. Thank you. Let's see. Paul is a project manager for MDA. MDA, of course, is the McDonnell Detweiler and Associates is the Canadian Space Agency prime contractor for robotics on the Space Shuttle and ISS. Paul will be discussing how the ARM can benefit from the state-of-the-art developments in the area of rendezvous and proximity operations and in satellite servicing domains. Paul?
Okay, thank you, everybody. So we started off looking at this problem. We had a good time, by the way, looking at this problem. But we broke it down the same way we would break down any satellite operation that we've done in the past. So we broke it down into rendezvous, proximity operations, and capture. Today's presentation is on the rendezvous and the proximity operations, and tomorrow I will be giving a presentation on the capture. So just to give a very quick overview, MDA has been focused on these type of activities for decades. So it started back in the 70s with the development of Canadarm or SRMS for the shuttle program, and includes significant rendezvous and capture of the Hubble Space Telescope 4 times from the shuttle. We've also actually captured the shuttle from station using Canadarm2 as well. Then we've done different developments, and I'll echo some of the sentiments of other folks here, but we provided scanning Lidar systems for XSS-11 and the robotic autonomous systems for Orbital Express. In recent times, the Canadian Space Agency has invested over $50 million in prototyping for what they call the next generation Canadarm. And in all of that, it has included rendezvous and proximity operations. So just to draw the parallels, and I know that everybody's walked through this as well, the typical operational steps include long-range and short-range rendezvous, scanning and mapping, rate matching, close proximity operations, et cetera. And just on the right, we're showing some of the heritage that we have in addressing that. So for the next section on the integrated sensor suite, focus on these aspects of the ConOps. So I believe the gentleman from Ball Aerospace had almost the exact same instrument suite, which I think is good. We're starting to synthesize. We're all starting to come together. What we were proposing was for far field, long range, to have a narrow angle camera that picks up bearing information. And then as you get closer, you actually combine the narrow angle camera with a Lidar. And the laser altimeter that MDA is developing for Osiris-Rex would be coupled with the narrow angle camera, which would give you bearing and range. And then as you get closer, you'd have a wider angle camera that begins to give you detailed features of the asteroid. And then that would be coupled with a flash Lidar. And MDA has been doing work similar to SLAM, or simultaneous localization and mapping. We have 2 coupled Funuk robots in a lab where we basically generate models using 3-dimensional and 2-dimensional data. We generate those models, we port them back and use the models to do close proximity operations. Also following down the concept of operations to look at close proximity capture and autonomy, MDA has done a lot of work not only in orbital robotics, but also in rover systems. And just to give you an idea of the state of the art, so on the International Space Station right now, there's the Dexter robot, or what we call the special purpose dexterous manipulator, and Canadarm2. And those robots are currently being operated from the ground. So to give an idea of where it's come to, originally they had to have the operator in the loop in close proximity. Now the ground crew is at Johnson Space Center or the Canadian Space Agency. The astronauts are asleep, and they begin to go and do all these dexterous tasks. At Goddard also mentioned the RRM mission, or the robotic refueling mission, that focused on unprepared and uncooperative capture, fill and drain valve refueling, and MLI blanket removal. And again, all of those tasks were done with 15 degree of freedom manipulator on the end of a 30-foot long Canadarm2 operated from the ground, all happening successfully. MDA has also been looking at low bandwidth, high latency situations. And we've had a variety of contracts with the Canadian Space Agency looking at variable autonomy. And variable autonomy, we consider it a spectrum, and it ranges from teleoperation to rigorous, rehearsed, scripted operations to supervised autonomy. Not dissimilar to how the Curiosity rover landed on Mars, that there comes a point where operator in the loop does no longer make sense via ground control. We've actually demonstrated this in conjunction with Boeing for Orbital Express, where the manipulator closed the loop with cameras as the proximity became closer and closer. And I don't have a concluding slide, just for the sake of time.
All right, thank you.
Okay.
We have time for questions, if any in the room or virtually.
There's a question here. Why the use? Why the use of both a scanning and a flash lidar?
So the it gives you your 6 degrees of freedom, instantaneous estimation similar to that of a video camera. And then you match that model with the model that you've created using your laser altimeter or your scanning lidar.
Okay, thanks.
Okay.
Any others?
I guess to follow up, why can't you use the scanning lidar for both?
I don't think I can answer that. I don't think I'm able to answer that for you.
Oh, okay. Go ahead, if you could go to a mic, please.
It's a quick one. No one so far has mentioned the use of automotive radars in the rendezvous. TIVAC were funded to do this under the Edison call last year, I believe. And it seems like it's a technology that applies.
Automotive radars, I don't think I'm qualified to respond to that.
Anyone else want to comment to that?
They tend to work at really high frequencies.
If you could go to a mic, it would be really helpful.
Automotive radars, they tend to work at, who asked that question? Anyway, sorry. Well, they tend to work at really high frequencies, and so they're expensive. But the rendezvous is mostly in the protocol, I think, a lot of that. So you can still use the antennas, and still use the circuitry and some of that.
Anything else? Okay, thank you.
David Gump is our next speaker. David is CEO of Deep Space Industries. DSI is focusing on low-cost scouting missions to characterize asteroid resources and developing in parallel the technologies to process asteroid material into useful products. His presentation outlines reasons for replacing the Keck-style return of a small asteroid with a mission that returns multiple samples from a larger target. The goal is achievement of better results for both science and industry while reducing several types of mission risk.
Thank you. The Keck-style approach, the baseline that NASA has now, I think has unacceptable risk for failure, because if all you're going on is the magnitude, the device and the mission you've designed for, say, 200 tons return could encounter very easily something at 500 tons or 1,000 tons. Even if your target has been considerate and actually flown by Earth for a radar observation, you still only know volume, you don't know mass. And the other point I'd like to make during the presentation is that scouting missions are really essential to bring down mass uncertainty as well as other uncertainties. We also believe that you ought to be fishing where the fish are. The vast majority of asteroids are not 7 meters in size. And for repeatability and sustainability, you ought to have a gathering of materials approach which is applicable to a vast range of asteroid sizes, not just the special case. And besides, it's just easier. and we ought to be going easier on this than making our life hard. To detect, to get enough photons to actually do characterization. When you're out in the deep dark, people have already pointed out that it's going to be hard to actually acquire for closing the target if it's an extremely tiny one. Large NEOs are easier to land on because they spin slower. And perhaps most importantly, Congress, your customer, has said they are interested in medium and large asteroids, things big enough to kill their constituents. They want them both detected and characterized, which scouting missions can do. We don't have any photographs of things a little smaller than 500 meters, and so we don't know if they do in fact transition from rubble piles down to monoliths, or whether they stay rubble piles down to smaller sizes. These medium sizes can wipe out Los Angeles, or really mess with Texas. So we think in general terms, because of all these questions, you ought to design the program, both for the retrieval mission and for scouting missions, before you leap into designing a specific mission. And there ought to be demonstrated a method that's generally useful and not limited to rare situations of small asteroids coupled with a billion-dollar SLS. That is not a sustainable approach, we don't believe. We think the basic program that we would propose would be modeled on COTS. You've now got 2 successful COTS systems in operation, as well as the ILDD that NASA has in place for the Google Lunar X Prize competitors. Very simple. You do fixed priced and below cost, so there has to be private investment. Competing companies get paid for achieving milestones and not just submitting monthly invoices. NASA would specify what it needs for its applications and its needs, and industry would fund the delta for everything else. In the fullness of time, most likely, NASA would be forced through budget requirements to go for a disposable spacecraft. Industry, to serve commercial needs ongoing, wants a reusable spacecraft. Industry would pay for the delta between what's required to support NASA's needs and what's necessary for commercial markets. And the resulting system then is sustainable, it's in place, it's serving commercial customers for propellant and for materials in orbit. If there's a year or 2 pause in NASA funding for asteroid missions, nothing comes to a close. The system is still ongoing. Another good thing about the gather materials approach is that the ARV size is independent of the asteroid size. You could do smaller ARVs in the early days to reduce mission costs. And the collection process can be selective. There are different colored boulders on Itokawa, for example. You might want to go for a specific color. You might want to go for sand and gravel because the processing step that you're going to bring it back to put it into would like it already crushed. You can gather the already crushed materials if you've developed at the beginning a gathering of materials approach as opposed to a swallowing of an asteroid approach. We believe scouting missions can collectively among them deliver as much material as Orion's 100-kilogram return limit. And they'll be coming from diverse sources, better for scientists, better for resource discovery. You'll get much richer data from that kind of approach to supplying things for the Orion SLS flight. We've done some of the initial math. On this chart, the vertical is kilometers per second delta V. We found as a rule of thumb the outbound delta V and the inbound return delta V are roughly the same. This is starting from C3 of 0 and returning to C3 of 0. You could launch a scout mission with that first arrow in 2015. It would get there a year later in 2016 at the second arrow. You gather some material. You get back a year later in 2017. And then you have a full year to analyze that material before you have to launch the retrieval mission with only about 2 kilometers per second required. It takes a year to get there, and then you have quite a bit of time before you have to do your return. You could actually return for less than 2 kilometers per second. That's 2001 GP2. This other one track we've done, 2013 BS45, is very convenient. You could do scout missions at several points along this track and still have time in the outer years to do your ARM mission, again, at a fairly low delta V cost. So we think that if you design this program so it serves both NASA and commercial needs, NASA will get the propellant and materials in orbit that it needs to make getting to Mars less expensive. Industry gets what it needs for its grandiose plans, and everyone benefits. It's synergistic. And in the short term, what we need to do is commission several precursors to do rendezvous and sample return missions. Previous speakers have described ARVs loaded with instruments just to find out what the mass of the target that they're already committed to getting would be. You need that information before you launch, before you've committed to that target. The other thing we think we need in the short term is a BAA for asteroid recovery mission ideas on how to gather material from any size NEA and how to structure it so it works on an industry-based approach. And finally, with ARV size unhitched from asteroid size, we should be optimizing for the least cost. It's very grand to set a really big technical goal like a gigawatt of onboard power for your iron propulsion. But if that turns out to cost you $1 billion a mission, you might do it once, but you'll never do it again. In the future, all of us will have to be much more sensitive to designing least cost combinations that can be sustained versus setting a technical goal that's really ambitious and hoping that in the fullness of time that results in a capability that can be used again. Thank you very much.
Okay, do we have a question?
Is there a business model for paying you by the kilogram?
Yes.
For return of sample?
Yes, on a per kilogram basis, will be a lot cheaper than Osiris-Rex. And it's valuable to both parties. We'll need samples for our own needs. We want to supply propellant to communication satellites, to transfer stages. A lot of the new launch vehicles that rely on air launch, they have a ceiling on how much they can launch using their system. If they can launch just to LEO and use a transfer stage that's space-based, refueled from asteroid resources, they gain a whole other order of magnitude capabilities. So we think there's a lot of commercial demand for what an asteroid industry can provide. Anything else?
Other questions?
Thanks.
All right, thank you.
Okay. Our last presenter in the formal agenda is a combination presentation by Bill Botke from Southwest Research and Robert Jedicke from University of Hawaii. Dr. Botke is director of the Center for Lunar Origin and Evolution of NASA's Lunar Science Institute and director of the Department of Space Studies at Southwest Research Institute in Boulder, also a flood survivor. And Professor Robert Jedicke is of the University of Hawaii and the Asteroid Terrestrial Impact Last Alert System, or ATLAS. The population of asteroids that are temporarily captured in orbit around this Earth, what Bill and Robert call mini-moons, are new and highly compelling targets for human exploration because of their proximity to Earth and their low geocentric velocities. They believe this population can help NASA address perhaps exploration's most problematic issue, that is identifying a near-Earth asteroid population that astronauts and their tools can interact with within cost and scheduling constraints. And here they'll briefly discuss what mini-moons are, what their orbits, sizes, and physical properties may be like, what can be done to find them, and how human and robotic spacecraft can potentially interact with them. And I will say they both submitted separate RFI responses, but the topics were so complementary we're having them present, and they graciously agreed to present together. So go ahead.
Thank you very much. Oh, well, Robert and I work closely together, so we're actually very happy to be talking together. So this is very different from the other talks I think you've seen this session. So far we've mostly talked about the ARM mission. We're going to propose a different mission. No one asked us. They should have asked us beforehand. But we think we have a mission concept for a human mission, which we're calling a mission to a mini-moon. And what we're excited about this is maybe one of the most exciting ideas I think I've seen in my career, in the sense that this has the promise to help achieve NASA's human spaceflight goals, but at lower costs and reduced risk than the things that are being presented today. So to give you a feeling for this, I have to describe mini-moons. So that means I have to give you something of a background on the near-Earth object population. So first of all, what are mini-moons? Well, let's start with sort of a top view of the solar system. So what you're looking at here in green is the main asteroid belt, and then you can see the orbits of the terrestrial planets and Jupiter out here. Now, the asteroid belt is the source for our near-Earth object population through different dynamical processes and the rest. The near-Earth objects are the objects here in red. These are bodies that cross the Earth's path, or in some cases come very close to the Earth, and they're what we're talking about today. Now, the ARM mission candidates are a subset of that population. They just happen to be the objects that are on very low eccentricity, very low inclination orbits. So they're really much smaller than this near-Earth object population. But what's interesting is while everyone's focusing on these guys, these objects actually do some special things. If you look at them and you think about something what we're going to call the Lagrange points. I'm not going to spend a lot of time going into the dynamics of Lagrange points. But essentially when you have objects on Earth-like orbits, they tend to spend a lot of time in special regions where the gravitational forces of the sun and the Earth are very comparable to one another. And so when you combine with the orbital motion, it actually creates a pathway where things can go in from orbiting the sun to actually going into orbit around the Earth itself. Okay? So this pathway is very interesting for the following reason. And that some asteroids actually enter into a Lagrange point, like L1. They rattle around the Earth-Moon system for a time, and then eventually they may escape out L2 or so. So these are temporarily captured asteroids. But the ones that we make a full orbit around the Earth, we call mini-moons. Okay, that's our formal name for it. Okay? But what's interesting here is that some objects are only temporarily captured over a short time scale. But others are captured over a much longer time scale, some cases up to years, even decades, depending on how you look at it or so. So this makes them very interesting targets for something we might want to visit in the near future. Okay? So this just gives you a feeling, also for the people on WebEx, just a feeling for some of the trajectories of these objects. Some are very simple. They just make one sort of orbit around the Earth. Some may make multiple passes. And then all of a sudden you can get crazy trajectories as these things interact with the moon and they interact with resonances with the Earth and the rest. You can sort of have a whole rogues gallery of things. Basically, the entire sphere of out to about 4 lunar distances can be filled with these objects. So the question is, how many of these guys exist? Okay, that may be one of the questions you want to know. To answer that, we had to do some dynamical studies. So this is some work done by Mikhail Gronvik and Robert Jedicke just over the last sort of recent history. What they did is they looked at the orbits of essentially the ARM candidates. And this is a plot on semi-major axis and eccentricity. And the numerical calculations to see how many objects would be captured over time. And I'll just give you the bottom line here. There's a lot I could say in this plot, but I don't have time. It's basically on the order of 10 to the minus 4 to 10 to the minus 5th of the population is captured at any given time. Or for those like to think of percentages, it's about 0.001%. So it's not very large. So what does that mean in terms of the entire population? Well, let's think back to the plot I just showed you. In white, I'm showing a plot of diameter in kilometers versus cumulative number. In white here, we have what we think the main belt asteroid population is like. In yellow is our best estimate of the near-Earth object population. Remember, that's just a sort of, in a sense, it's a dynamically escaped subset of the main belt. From there, we have the population of ARM candidates. That's just a subset of the near-Earth object population. So if we take that best estimate we have for the ARM population, and we multiply it by about 10 to the minus 5th or so, we end up with a population of model mini-moons. Okay, so these objects, there's not a lot of these guys, but they're in steady state. So at any given time, there's several meter-sized guys to visit in the Earth-Moon system. So what does that mean? What's the bottom line on that? So essentially what we're talking about is a few objects which are maybe on the order of a washing machine or so. Okay? We maybe have a dozen objects or so, which are maybe about the size of a beach ball. And then every once in a while, we have a larger object. Okay? So they're not very big, but there's always something to go visit. Okay? And ultimately, we're reasonably happy with these numbers, but we'd like to do more observational work, and Robert's going to talk about that, and a better theoretical study to understand this. But even so, these objects are very interesting from a science perspective. Okay, so how long do they last? Typically, our numerical simulations suggest they last on the order of about 3 orbits around the Earth-Moon system, or about 10 months. And you can see here there's something of a long-lived tail where they can last much longer or so. So that's pretty short to think about a human mission to these things. But keep in mind, if you had a robotic precursor go out to these objects, you could very easily stabilize them. It doesn't take much of a velocity kick to actually put them into an orbit which will last 100 years or so. So in a sense, you can think about them almost as a mini arm being able to do lots of interesting things here. Okay, so I want to close my portion of the talk just by saying why these things are scientifically interesting, why we might want to go see these guys. So the first of all to understand is that these objects are essentially the precursors or the meteoroids that are delivering meteorites to the Earth. And so you have a sense, you can get samples that are outside the atmosphere before any contamination or anything else has taken place. And they can actually tell us about the original building blocks which made the planets. And they also provide information on possibly how life got going, depending on if you get organics and volatiles and all the rest. This is a major NASA goal, and that's demonstrated by the Osiris-Rex mission that's out there. There's also the fact that these samples can be very large. And if you like it, you can bring the entire thing home, depending on how you want to do it. And that's a key goal regarding the study of asteroid resources, and we've already had talks on that. Finally, there's something else to keep in mind. While everyone talks about asteroids being rubble piles versus solid objects, there's one more issue to keep in mind. All of the asteroids we're dealing with are small enough that essentially, in some cases, they may literally be held together, not by necessarily gravity, by electrostatic cohesive forces. This is becoming more and more recognized in the small body community. So some of these objects may literally be sandcastles. And if that's true, it'd be very important to understand that nature before we send humans out there to interact with them in some fashion. And so a mission to a mini-moon can buy down risk by understanding these objects. They're natural laboratories to understand these really poorly understood processes. And so with that, I'm going to hand it over to Robert, and Robert's going to tell you about how we can find these guys. So, go ahead.
Thank you, Bill. So I'm sure you're all wondering, just a couple theorists standing up here talking about this these vapor moons up there going around the Earth. Can we actually find them? Are they actually there? And the whole idea started up about 20 years ago when I was working at Kitt Peak, Arizona. I was working with a project called the Space Watch Project, looking for asteroids. And every once in a while, we'd find a geocentric object, and it would have this very elliptical, high inclination, high semi-major axis orbit around the Earth. And I would report it to the Minor Planet Center, and they would write back to me saying, oh, Rob, don't worry about it, it's a geocentric object. I said, what if it's a natural geocentric object? It's a very strange orbit. They said, oh, there are no natural geocentric objects other than the moon. They said they're all artificial. And I thought that was very odd. So 20 years go by, and a couple years ago I found this postdoc who was willing to work with me on this project, and we did the simulations and actually figured out that, yeah, a very small fraction of the population can go into orbit around the Earth, and they can be captured by the Earth-Moon system. Unfortunately, we published our paper a few years after the discovery of the first mini-moon, 2006 RH120. If only we had done this 10 years earlier, we would have predicted this object. And the great thing about this object is it's really a poster child for mini-moons. It's pre-capture heliocentric orbit. It's post-capture heliocentric orbit. It's geocentric orbit. We're all exactly what we predicted in our model. The duration of time that it spent in orbit around the Earth was the average of what we predicted mini-moons should spend around the Earth. Basically, everything it did was right. Even its size, at 3 meters, which is about the height of a typical high diving board at a city pool, right? Even its size is about the right order of magnitude that we expect from our modeling. When an object like this goes into orbit around the Earth every 10 years, the surveys have been operating for 10 or 20 years at different levels of efficiency. So it's about the right order of magnitude for us to be finding these objects. So it was the poster child for mini-moons. It was found at the time because it was bright and very slow moving. And so it was relatively easy to find by the Catalina Sky Survey. But this is just, we think this is just the tip of the whole mini-moon iceberg. We think there are many more out there, and we think we know how to find them. We've done a lot of simulations using different assets on the ground. If you're on the ground, you want to probably be using visible light. You would really like a survey that's got a wide field telescope that can get to extremely faint limiting magnitudes, that can take very short exposures. So something like the Large Synoptic Survey Telescope that should be operational about 5 or 10 years would be a really premier instrument for finding these mini-moons. But that's still a decade or so in the future. Right now, there is an asset available, the Subaru telescope, 8-meter telescope on the summit of Mauna Kea, Hawaii. And they're just installing the Hyper Suprime camera. And this is a phenomenal instrument. And we think that if we had time on this telescope, we would be able to find mini-moons in a regular way. We think that there's a 40% probability of finding a mini-moon on any night we go observing with that telescope, which means that there's about a 90% chance of finding a mini-moon if we had 5 nights on the telescope. The one missing key is that it would require a wideband filter that's optimized for the detection of these mini-moons. Right now, they use relatively narrow band filters for doing astronomy and astrophysics, and for doing asteroid science or discovery, you want it very wide. You want to basically let in as much light as you possibly can. But if you really want to find a lot of mini-moons, dozens at a time, you want to go to space. So we've done simulations from space, and we think that if you're going to go to space, the best place to be would be at L1. L1's a location about 4 lunar distances away from the Earth. It's in the direction of the sun, so you're looking sort of back towards the Earth, and you're going to see the mini-moons sort of distributed around the Earth, as shown in this figure here. If you put a 1 meter diameter mirror with an infrared camera at L1, we think that there would be 30 detectable mini-moons on the sky plane at any time, so that you'd have dozens of mini-moons that were available. You could, they're going to come in and out of visibility, so that over the course of a month or 6 months or a year, you're going to see many, many dozens of mini-moons, and that's extremely interesting to us. It's also interesting to us because 1 in 100 mini-moons actually become large bolide meteors, right? So that you can find these things before they strike the Earth. And then you get the side benefit of if you have a spacecraft like this at L1 looking back at the Earth, it's really a early asteroid impact warning system as well. Just like you've got satellites up on orbit around the Earth looking for hurricanes and tornadoes, this would be an early impact warning system for asteroids. So not only are you finding mini-moons, but it's an early impact warning system. So if we find them, can you actually visit them? Those orbits that we showed look kind of like crazy straws, right? And so I worked with a mathematician at the University of Hawaii who was quite excited about doing calculations to see whether or not you could actually devise orbits to these crazy straw objects. And what we found, actually, is that what we first of all started simulating was we thought, well, these things are only in orbit for 10 months. You can't possibly get a mission up and running and send it out in 10 months. So what we thought instead is let's put a spacecraft in geosynchronous orbit and just let it stay there and just store it there in hibernation until we find a mini-moon. Once we find a mini-moon, so we got the spacecraft here in geocentric orbit, and once we find a mini-moon, as it's coming into the Earth-Moon system, we sort of triggered the spacecraft and we say, okay, now we have the orbit for this object, we've bounced radar off it, we've got a great orbit, we can deorbit it from geosync and make it rendezvous with the asteroid. We can match its speed and velocity. And we found out that every single one of the 17,000 mini-moons that we created in our simulations, we could actually get to with this kind of a scenario. Now we're working on different scenarios, looking at storing the spacecraft at L1 or L2 to see whether or not there's any difference. Our preliminary work suggests that it's possible to get to the mini-moons, all the mini-moons, even if you're starting at L1 or L2. For human mission planning, you'd probably want a mini-moon that was on a longer term orbit. You wouldn't want something that's just there for 10 months. You'd probably want something that was going to be there for years. So you might get lucky, and you might find one of these mini-moons that are in a long-term stable orbit, or you could do, as Bill suggested, that you could launch a precursor mission to go and stabilize a mini-moon orbit to make it stable for centuries or so. At that kind of level, you should be able to have an Orion, a mission that you could get to with Orion spacecraft, sort of in a 2 to 3 week time frame. So these mini-moons are at sort of the distance of the moon on average, right? So it's about the same amount of time as it takes to get to the moon and come back and have a mission to the moon. So we're talking about very reasonable time frames for manned missions to these mini-moons. So we think that mini-moons offer a lot of advantages. They offer a great way to test ARM technologies. I mean, I've been really impressed by all the great ideas you guys have been talking about. And I think that all of them can be applied more easily to the mini-moon idea. These things are right in our backyard. They're going around the Earth. They're extremely low delta V targets. They're smaller asteroids, so they're easier to capture, easier to bring back, easier to de-spin. And scientifically, it'd be extremely interesting to bring back an entire intact 1/2 meter or 1 meter diameter asteroid, bring it back to the Earth. And the interesting thing is the mini-moons are detectable with our existing assets. We just need to apply something like Subaru telescope to finding these objects, or we could be a little more ambitious, develop an asteroid impact warning system, put it at L1 that will also find the mini-moons for us. So at the very least, we think mini-moons warrant an in-depth study to determine whether or not they're useful for the spacecraft industry. Thank you. Thank you. Any questions for Bill and Robert?
Yeah, you said of the 17,000 in your simulation that all of them, you could get to them when leaving from GEO. What was your delta V limitation on getting to them?
It was a couple for a few kilometers per second.
A few kilometers, okay, thanks.
So GEO is the wrong place to wait.
Yeah, we know that now. You might repeat the
comment.
Yeah, we know that now. We've since learned, and we're simulating what would happen if wait from when we're waiting at L1 or L2.
And how much delta V does it take to stabilize the asteroid itself?
Do you know that answer to that?
That's a really good question. It's a real.
Repeat the question for the guys.
Okay, so the question was how much delta V does it take to stabilize these mini moons? The question is we don't know because we haven't gotten the funding yet to do that study. If they fund us, we'll let you know. But typically, what you can think about though is you think about the difference between the mini moon orbits we showed and then the long-lived tail. It doesn't take very much velocity to put them onto a long-term stable orbit. So I would think the velocity requirements are going to be very, very small. So you could think about even doing this in rather than putting some mechanism on it, you might even be able to do this by a gravity tractor in some sense. In some cases, we're talking about small enough objects that that's very viable to do. So there's all sorts of possibilities we could think about.
How many of these objects have, I know haven't been looking for them very much, but how many have been cataloged?
One.
Just one?
Just one object. And that even that is very consistent with our models, with our simulations. So we've taken our mini-moon model, run it through simulations of existing surveys to predict how many would be found, and the answer is basically the one object that was found. Because in order to find these things, you need to design a specific strategy. The asteroid surveys that are in operation right now are not really looking for these things. In fact, we think probably a project like Pan-STARRS that I used to work on has probably detected these things. But just detecting something is different than discovering and realizing it's a mini-moon, because mini-moons have got different sky motions and different properties, and they're more difficult to link than heliocentric asteroids that are much further away.
What about your data from 20 years ago?
Yeah, I've thought about going back and looking that up. The thing is that with those objects, we only had, what would happen typically is we would track them for a few hours on one night. And then we'd send them into the Minor Planet Center, they'd say, don't worry about it, and then we'd stop it. We wouldn't bother looking at it for the next day.
There was perhaps another aspect to consider is that near-Earth object surveys are strongly discouraged from tracking geocentric objects for reasons that have to do with space surveillance issues. So only recently people have become aware that maybe they should consider other possibilities.
There's also another possible detection of mini-moons. At roughly the same time that we were finding these things at Spacewatch 20 years ago, the Air Force did a radar survey looking for objects. And they found, it's recently been declassified, and they found 3 objects that were on extremely unusual orbits that they did not think were consistent with any artificial known satellites or even debris from any satellites because the orbits were so strange. However, those orbits are extremely like mini-moon orbits. And at the time, they speculated whether or not they could be natural objects, but nothing was done about it.
Okay, anything else? All right, thank you. All right, now we've navigated the first portion of our program on time. It's 4:15. What we have left is, first of all, there was one presenter, Joel Surcell, who had a presentation in another session that he really feels like belongs here, so I want to give him 5 minutes or so to be able to give a brief talk of that, and Romero would like to ask your help for that. We also need to go back and address some of the questions since several of the first presenters didn't have a chance to receive questions. And then the third thing between now and 5:30 is to talk through some key the preparations for Wednesday's outbrief. And we have a start at that we'll talk from. So, but I think as long as it's been right here, I think at the risk of losing the audience, we'll take a short break for 10 minutes and try to get back here by 26 after so that we start at 4:30 prompt. Thank you. Yeah.
this is a NASA thing. We've been able to set it later in October, and he said, and it will come everybody was doing it a lot first thing. As a project, we've been selling on Skype. There's no way the weather is full dynamics.
Hi, good, thanks. How are you?
How you doing, Ron?
Smart company.
And I was wondering when NASA was going to have a
tomorrow, maybe coming my way or something, I-59 or something.
Might not be able
How
to
does
find
that
out.
message relate?
Go back and not don't have any good life after. Definitely shut down.
Right. Well, I'm
The Keck approach to find an asteroid, bring it back, send
around there.
Check that out.
I'm like, I was just amazed. Space.com about that today. Slam an asteroid to the moon. NASA slams that to the moon. We're going to reconvene in 4 minutes. What do you think we're going Yours will come over. Should be a 10-second. So we were talking about Earth Moon L4, L5.
The room or sit down, please.
Been over a decade in the making.
Either one.
Now it's just
No, that's good. All right. As we said, we have one addition for a short discussion by Dr. Joel Sercel. He's his paper's in another session, but it really fits better here. So we're going to give him about 5 minutes to talk through that. Then we'll go back through some of the questions that we hadn't gotten to, and then we'll talk through what we want to talk about on Wednesday. Dr. Sercel is the president and founder of ICS Associates, which specializes in helping clients become more innovative and effective at systems engineering and project management. Joel has over 25 years of experience developing advanced technology and innovation products. He spent 14 years at JPL and 2 years as a senior program manager for the Air Force. Joel received his PhD and master's in mechanical engineering from Caltech with his doctoral dissertation in space propulsion plasma physics. Joel?
Thanks very much. I really appreciate the possibility of letting me go today. I'll go fast because I'm not going to say much. I'm not going to tell you what our concept is. Sorry about that. I'm going to give you some parameters about it. It's a powerful idea. It's not the kind of idea that you just tell people before the business has been put in place. One of the co-architects of this concept is James French, who you may know from being the architect of Blue Origin's satellites. He was also the chief engineer of AMROC, the company that made the hybrid rockets that are in use in Virgin Galactic systems. Another person who worked with us is Greg Marinak, who was one of the co-founders of the X Prize Foundation. So we're very excited about this. It's a radically different approach for near-Earth object redirection. I'm just going to tell you a couple simple things about it. Number one is, what is the goal of it? We call it Honeybee, not to be confused with Honeybee Robotics, which is spelled differently. Or there's a Bumblebee asteroid deflection system that they've been working on in Scotland that's not presented here this week. Because it basically goes out and gathers things in a way that's analogous to bees. And that's all I'm going to say about the technical approach. I'm going to say why we're doing it. It's very important to ask the question, why are we doing this? I think ARM is a very cool mission as currently conceived. And the why that NASA has is to give astronauts something to do. That's really cool if that's what you want to do. But we have a different goal. And it may also give astronauts something much more powerful to do. So I'm going to give you a description of the mission attributes. This is the why. This is the how. What I'm not going to do is I'm not going to give you the what. How does it work technically? That has to go for another place. Talk a little bit about what it would take to be successful from the larger perspective. And I'm going to tell you how to contact me if you want to discuss the proprietary systems and approaches. Because when we do this, it's going to change everything about everything in space. So why? The goal is simple. To make humanity a species that uses extraterrestrial resources for practical purposes. But not to do it with pie in the sky. To do it with a system that today, every element of the system is at TRL 4 or above. And to pilot, that means to really, no kidding, do it, an affordable method to use in a practical way hundreds of tons of extraterrestrial resources, which Honeybee does. To radically reduce, and once we do that, it will radically reduce the cost of space operations for all kinds of further missions. So for example, when Honeybee is in place, we will have demonstrated the ability to essentially convert a 1,000-ton NEO to a propellant depot that could be used to fill the tanks of a manned Mars mission at the top of the gravity well. That collapses the cost of human exploration of Mars. It allows you to put in place an inexpensive transportation system to go anywhere in cislunar space, which includes LEO to GEO. Therefore, a Falcon 9 would have the ability to launch 2 5,000-kilogram GEOs, and that's the big class, and a 2,500-kilogram GEO, all on one Falcon 9 launch. So someone who is in that business, tell me how much that saves in launch costs. I don't know the number. I'm assuming it's somewhere in the 10 to the 8th dollars. What does Honeybee do? It captures a NEO into cislunar space, a lot like ARM. But it's radically different in the sense that it uses very simple, common sense systems, nothing nothing very high-tech or advanced. There's no high-power electric processing. There's no 50-kilowatt solar array. There's no plasma propulsion. And John Brophy remembers when we did NSTAR. I mean, I'm a big, passionate believer in electric propulsion. I just don't think it's the right choice for this mission. However, unlike ARM, it does require careful selection of the target object. And so I'm a big believer in the talk that Mr. Gump gave that said you have to do prospecting first. I used to have a manager who used to assign me to do PowerPoint presentations. And we called it the Bring Me a Rock PowerPoint method. He'd say, I want a PowerPoint presentation about something, I don't know what it is. So I'd bring it to him, and then he'd have me redo it 100 times. We called it Bring Me a Rock. Bring Me a Rock may be a way for managers to get PowerPoint presentations done. It should not be the way that NASA plans a multi-billion-dollar mission. So at the technical level, if you compare Honeybee to the baseline ARM mission concept, instead of delivering, and John, I read your different papers, there's a little spread in the data in terms of the cost. It's an evolving concept, that's all good. Instead of delivering in round numbers 15 tons, by the way, ton is T-O-N-N-E-S. I notice a lot of typos on that in people's talks, and I'm bad at spelling. So instead of 15 tons to a low C3, you require only about 3,000 kilograms to a low C3. Instead of a long trip time out and back, it's short. And it's short, I won't tell you exactly how, but it's more like a very impulsive trajectory. Probably reduces the cost a lot, and then interesting, switching from Mac to Windows distorted the formatting. But anyway, instead of returning a 1,000-ton object that now you got to figure out what you're going to do with it, it returns the object in such a way that we have a functioning, fully functioning orbiting propellant depot. How to get it done? I totally agree with Mr. Gump's point on this. It's got to be about public-private partnership, a combination of venture capitalists, aerospace companies, NASA, and JPL. I think that's the right way to do it. What we need to do is we need to pull together as a community to understand it's time to stop screwing around with high-paid tourists that we called astronauts in space. It's time to start doing something really important in space. And this is the beginning of that process. So what I'm asking you to do is I'm asking you to think not like a 20th century enterprise, but like a 21st century enterprise. And if you're interested in finding out about it, we can talk about it under NDA, and that's my contact information. So thanks very much. I appreciate it.
All right. Any questions for Joel? Quick question for Joel? We'll go on to, okay, then we'll go on to revisiting. Romero, could you bring up the introduction presentation?
My contact information is up there. I'll be glad to write it down.
And then if you would go ahead, 2 slides. Just as a reminder for, this will also be a good place for us to start when we get through this, the question. So what I'd like to do is see where we get to in the next 15 minutes or so, or if we don't have enough questions, we'll go into the next phase. But so does anyone want to bring back one of the presenters or bring up a point? We do have several from the chat, and we can start with those unless somebody has something. So go ahead, Heather. If you'd go to a mic, you can go to you can have this one if you want. I'm glad to have this.
Okay. So I'm going to just start at the beginning. So John Brophy, there was someone who addressed, does the material of the bag need to be electrically conductive to prevent static charge buildup?
Yes. Yes.
Okay, well that was quick. All right, don't sit down. Don't sit down. You got a couple here. So somebody wants to know how you match the spin rate of an asteroid.
Okay, so to match the spin rate, you just have to, there's attitude control thrusters on the spacecraft, and so you just use that to spin up the spacecraft to the same rotation rate as the asteroid.
We're matching the instantaneous rotation rate. You might want to clarify.
Yeah, I mean.
Watch the asteroid.
Yeah, okay, so people are adding more detail. So we watch it long enough to be able to know exactly its spin characteristic and project that into the future, and so that you can then match the instantaneous spin rate at the time you're going to go grab the asteroid.
And that's for high spin rates, right? For lower spin rates, we don't even have to bother with that.
You sure that question was for me?
Hey, you were presenting, John, so you were the lucky one. Okay, so then there was like 4 or 5 or 6 different comments that came in about electromagnetism. So I'm going to just kind of describe in general what they were, and then we can have that discussion. So should electromagnetism be used as a backup to the capture bag to secure the asteroid? Magnetic components within a bag could help de-spin. Concept generate electromagnetic charge for tow and capture. What about a tractor beam?
I like the tractor beam.
So let's see. Those were sort of the gist of the electromagnetism, but there were quite a few different threads about that. So
okay, so I think the notion is, can you use some kind of electromagnetic forces on the asteroid to help control it or detumble it, and that requires you to know a lot about the asteroid and how conductive it is and how how you can apply those forces. So probably wouldn't be the first approach that we would attempt to capture an asteroid with.
There was a question about if you were attached to a nickel-iron asteroid, could you chemically produce hydrogen for fuel?
No, no. I mean, but it would be awesome to find a whole nickel-iron asteroid. Yeah. But we probably wouldn't bring that back.
Let's see. All right, we talked about that one. There was sort of a discussion, and there really wasn't a question that came out of it. There was a discussion that might be worth capturing about the trade between designing a vehicle for worst-case masses when you have large uncertainties versus funding robotic precursor missions. So there was quite a few different threads about that, and in discussing with Jim, he thought we ought to just capture that as a...
Yeah, well, that is that's a serious issue, and that is one of the key drivers for the characterization, the observation campaign, the characterization part of that campaign. And so you have to do the right characterizations to limit the uncertainty in the size and mass and spin state of the object, so that it's within the capabilities of your flight system with appropriate margins. And in the analysis that's been done in the study period over the last 7 or 8 months, it's clear that such an observation campaign is possible. And part of the reason for that is, someone had mentioned in one of their talks that there weren't a lot of these small objects, but the current population models, suggest that basically all the near-Earth asteroids to first order are small, and there are just a scattering of larger ones. And so there are lots of objects potentially to discover and characterize, so that we can, as I mentioned earlier, there's the likelihood that we'd have 15 to 20 good, well-characterized objects that we could return.
There were a few comments about having the mission thought out further for better integration and long-term purposes for the asteroid. Just a couple along that thread. And I have a couple of my own. That was the end of the virtual ones.
Okay.
If that's okay. So the one was for Boeing, and I was wondering what updates you've done to your AR&D sensor suite since Orbital Express.
Yeah, please. There's one over there if you like.
Actually, we've done quite a lot. As I mentioned, we're developing the Vesta system for commercial crew, and so we are headed for a critical design review on that system here in December. So that's that could give you a sense of the maturity. So the sensors, 3 different sensor types, are in development. The ones I talked about in the presentation there. Beyond that, we've done quite a lot of work on the software. which we call VisStar, that initially flew on Orbital Express, and since then we've been maturing that software to make it specifically applicable to the International Space Station. And so a lot of the track modes that there have been papers written, you can look at this, but the different track modes that we had on Orbital Express are now being updated, including specific feature track modes that are applicable to station. And those modes are also applicable to natural bodies. The sorts of, you're looking for features, they don't have to be any particular feature, so there's a lot of flexibility there in terms of what the details of those features are. And we're also doing integrated testing in the laboratory, and that's going on today. So a good bit of what I talked about, there's actually hardware in the lab today and software integrated in the lab today that's doing testing on an optical range. That give you a
And
general
are they
idea.
the same exact sensors, or you've updated them, the same class, as I understand?
They are updated from what we flew on Orbital Express, yeah.
I have a follow-up. It's I think that you mentioned one of the sensors is a 3D Lidar. Is that scanning or flash or?
Yeah. So at this point, let me just say that I'd probably like to not say right now, but
Okay. But you didn't have one in Orbital Express. I thought Orbital.
we had a Lidar on Orbital Express. We had a rangefinder that was a scalar delivered to scalar range.
Okay.
And so this is a
rangefinder.
this is a 3D this is a 3D sensor.
Thank you.
All right, my next question was sort of general. There were several AR&D sensor presentations made for sort of a suite of sensors, and I noticed some contained IR cameras and some contained only visible cameras, and we've had a lot of discussion and debate about that, and I don't know if it's appropriate to just capture it, or if anyone in the room wants to comment about who did include an IR camera in their suite, the benefit of that versus just the visible camera. And there are certain obvious benefits, but if anyone wants to address that.
So since I'm standing at the microphone, I could start by saying that we include a long-wave infrared camera as part of the suite. And I sort of said why, but the ability to track at night or in poor lighting when the or at low sun angles is a good reason to have the LWIR camera.
Okay. Other questions? And Heather, have there been others come in? Oh, we have one. Go ahead, and then you.
For the baseline ARV vehicle, we've seen some engineering sketches. Can anyone describe what tonnage it's designed to retrieve or what delta Vs it achieves outbound and inbound? There was no discussion of that.
Okay, yeah, so for the, I feel weird talking. I'll do this. Okay, so the for the baseline vehicle, it was designed to return asteroid masses up to about 1,000 metric tons. And I say about because it depends a lot on the specifics of the asteroid and its orbit and the characteristics, and also on when you can launch and what launch vehicle you use and so forth. But so, you know, roughly 1,000 metric tons is the limit. And it uses, we can store up to, as I said, about 10 tons of xenon and 400 kilograms of hydrazine. So those all fit into that, as well as the capture mechanism size. They're all interrelated to some degree.
Inbound and outbound delta V.
Oh, I'm sorry. Yeah, the delta V. So the inbound delta V is on the order of 100 to 200 meters per second. That again depends on the asteroid, and part of that goes to getting the asteroid into the long-term DRO after the lunar gravity assist. The outbound delta V depends on whether you're spiraling out from Earth orbit or just doing the heliocentric phase, and so it could be on the order of 4 to 6 kilometers per second, maybe more, depending on how low in Earth orbit you start.
Questions? Do you have? Yeah, no, go ahead. You go ahead first.
My question is to some extent rhetoric, because it is addressed to the whole community. And this question is why as a target orbit was chosen the cislunar orbit, because some other alternative option do exist. For example, we can transfer the asteroid, the target asteroid, into orbit synchronous with the Earth's orbit, with period, for example, 1 year. And in this case, the delta V needed, it was checked, is only several meters per second. And we can reach this asteroid in the ideal case 2 times per year. And the arrival delta V will be almost ideally 0, and departure also almost 0. Thank you.
All right, well, I'll take a crack at that. We talked a lot about where to deliver the Asteroid to, and the selection of the distant retrograde orbit around the Moon appeared to be a good choice because it was an orbit that both the asteroid retrieval vehicle with a 1,000-ton asteroid in tow could get to for a reasonable delta V, and that could be, and it's stable for a long time, on the order of centuries, and that the SLS and Orion could reach with multiple opportunities per year. Oh, okay, yeah. And if you lose control after a couple hundred years or whatever, yeah, it won't hit the Earth. Even though it's of a size, it's not a hazard. It's kind of a belt and suspenders approach to safety.
All right, another question?
Yeah, everyone's picking on John here. But my question is also to you. A question I'm sorry. But I was curious, though, about the dependence on the ARM mission today in terms of the synodic period of the asteroids, in this sense, and that you probably have a launch window to launch ARM. Okay, so then you have to go after this asteroid. But if you miss it, the synodic periods of these objects are such that you're never going to be able to go back to that one again. So how many backup targets do you need to make sure you can fulfill your mission?
One, no. So, I mean, that's a really good point, and that's why what you really want, what you need for a robust mission is to have multiple backup targets in multiple years, because the programmatics are such that we're not sure when you could launch, or if you run into technical difficulties and you have to launch 6 months or a year later, you need to have a robust series of targets in multiple years that you can go to, and that's why. So because of the synodic period problem, if you miss it, you got to go to a different target. Yeah. Unless it depends on it's not quite that black and white, because if you change launch vehicles, if you plan to fly on an Atlas V, for example, and spiral out from Earth orbit, if you miss that launch and you have an opportunity to launch on a Falcon Heavy, for example, and you can then make up that year to year and a half slip by eliminating the spiral out time and going directly. So you have some flexibility there as well.
You may want to talk about the launch window in the same sense, because SEP does change the dynamics of that significantly.
Oh, you may want to repeat that for the WebEx.
So and Jim's right. So the other part of this is with electric propulsion, you get a longer launch period than you normally get with ballistic interplanetary spacecraft. And so you have additional flexibility. Dawn is a good example of that. I won't bore you with all the details, but at the very end, it was going to launch in the beginning of July, and it wound up launching at the end of September, but it could still do this multiple main belt asteroid rendezvous mission because of the use of electric propulsion. So you get that added flexibility as well.
Okay. Any other last questions? One last one.
Yeah. We've been talking a lot about solar electric propulsion, and one of the comments early comments was launching into a highly elliptical orbit. We've been looking at small orbital debris, and it's getting a whole lot worse. And One of the things that we looked at was that a highly elliptical orbit, like we're planning for SLS, the first couple of missions, gets you out of that problem very quickly. But I've heard a lot of comments about the Van Allen belts and trying to avoid exposure to that. Has the small orbital debris exposure, which is getting worse and worse as time goes by, has anybody been figuring that into how they do their launch to avoid having to slowly spiral out through the shooting gallery?
All right. So, so the reference mission that we spent most of the time on launches directly to the lunar gravity assist, so eliminates that problem entirely. There is a wide range of intermediate orbits that you could launch to, including GTO and other elliptical orbits. But we haven't spent a lot of time looking at the orbital debris problem. We did spend a little time looking at the radiation degradation on the solar arrays and the need to make them bigger to accommodate that. But certainly, if that were the option of choice to launch on an EELV and spiral out from some elliptical Earth orbit, you would definitely have to accommodate or make accommodations for that orbital debris issue, or make sure that you understood it.
Okay, thank you.
Room for one more?
One more.
I think this one is for LMA. I think LMA mentioned some sort of a concept about laser measurements that I wasn't familiar with. Is some holographic something? Can you explain a little bit more what that does and what it is? Is it a point cloud, or is it?
Do you want to try? Unfortunately, no. I don't have enough knowledge of it. Sorry, but I can put you in touch with somebody.
Is that something that is a new concept, or this is something that?
It's something they've been working on for several years now. Mostly for terrestrial, but it's also they've been looking at applying it since.
Okay. All right, thank you. We come to our last item, but it's a big item for our last 30 minutes in this session. And I just want to remind us what the purpose of the Wednesday session briefing, what's being asked of us. And there were 5 Michelle talked it this morning at the plenary, but there are 5 main categories that we were asked to present. What our session purpose was, what our RFI selection process and agenda. We've talked those already in here. We'll make slight mods to the agenda, but we basically held. And then key topics discussed and findings. Oh, and I forgot to get the. So can you? So we tried to put together. Okay. So we have about 4 charts that we put together, a few of us, just based on having read the R5s, just for a starting point for the audience, because otherwise 40 people creating 4 charts probably doesn't work so well. But so the first part of that is, and I should add a little more. The first part of it is what key topics did we discuss, and then what findings. And for findings, what we're asked to provide is a summary of the most promising ideas, including their innovativeness and potential for improving mission system performance and affordability. Any technology development needed to mature the ideas to the point where they can be incorporated into system designs. Relationships or linkages between the ideas that could help with mission system concept integration, and further studies or next steps. And I will admit that when we put this together, we didn't have guidance. So they probably don't match quite exactly. But we'll go through it, and as we'll just kind of talk through it and open it up for comments as we do. The first thing we thought we would do is, and again, some of this we may be off on how we did it, because it may not have been quite talked as we were going through it. But the first thing we did is kind of divided our topics into these 5 categories, and then on the next 2 charts, we'll talk a little bit more detail of each of these 5. But we kind of heard a lot about vehicle systems, use of spacecraft buses, that kind of stuff. There's a large category in sensing systems and algorithms, mission enhancements to the base reference mission, extensibility considerations, and alternate mission scenarios and concept of operations. We'll go through them next, but does anybody have any comments at this point? Do they sound about right for the types of things we heard? It's kind of hard as rushed as we were through this, so I realize how hard that is to do. So,
I guess I would comment that I heard an awful lot about different business strategies. You know, it's sort of, I don't know if it fits well with everything up there, but there were different ways of structuring how we do this, not necessarily the specifics of what we do, right? And that I thought that came through in several of the items today.
Any other comments? That was a good comment. Go ahead, John.
Yeah, I have one comment that seems a little counter almost to the innovation and everything else that we mentioned, which is there was a theme throughout all the presentations, which is that for most of the areas, it seems like there's a broad base where we can leverage existing assets, capabilities, and expertise, and then we won't need to rely on lots of technology development throughout the overall mission. And in the areas where there is a lot of innovation, you know, that's where they'd be looking to NASA.
I'm thinking both of those really fit under most promising ideas that help to reduce, improve system performance, and contribute to affordability. Both of them could show up under that first bullet, couldn't they?
And what first bullet are you talking about?
The first bullet in findings. Is this turned on? Can anyone hear me? Yeah. Okay, sorry.
Okay. All right, any other comments? All right, let's step through what we had. In vehicle systems, we had discussions on key technology readiness areas, solar arrays, thrusters, power processing units, adaptations of existing spacecraft buses, the balance. I don't think I heard this so much as we saw it in the papers, we thought, but we can talk about whether we felt like we did. Balance between technology development for improved mission versus oh no, this one we certainly did. Use of low-risk, mature technologies. That was kind of the comment that John made. What I didn't hear necessarily was a talk about a on-ramp versus off-ramp philosophy. Do you start with something in on-ramp technologies, or do you start with something and then have off-ramps? Certainly the plan we have right now is to pick some medium level and off-ramp if need be, as opposed to trying to on-ramp it, especially if our target schedule is what it is. So, and then key risk and development areas, asteroid characterization, rendezvous and capture system, solar arrays, high-power thrusters, power processing units, although really we hear talks about that being fairly mature, so maybe that shouldn't be on this list, but we can talk about it. Xenon tanks, dust and volatiles. So I'll stop there and just kind of open it up to discussions on, does this adequately capture things, and are there things we should remove or add?
Yeah, the one thing I think that probably needs to be added to that I heard in a number of the presentations is that there is a good variety of capability for simulation and test of many of these systems on the ground in the lab. So I think that need to capture that as well.
Okay. We'll see if we have that somewhere coming up. I don't think we do, though. Any other comments on this?
I think you can take off PPUs.
Yeah, PPUs I think we can take off. There was discussion on xenon tanks, but it's really a go design, not really a technology or a key risk area. Does anybody think?
There's still some out there that think that we should leave the power processing units, I think,
okay.
for what it's worth. There was at least the European talked about something other than Hall thrusters, and we've seen that a couple of times where the discussion was, can we do, other plasma-based SEP? I think we're going to run into a technology timeline difficulty with that, but it was definitely brought up as a discussion point.
That's true, and it has some very interesting features, but as you said, and as Abe pointed out, the TRL is still something that makes it challenging, but it's a good thing to bring out. Anything else? how this is going to work. Yeah. Would you go to a mic, please? Thank you.
I think one of the key things in the vehicle and the sensing systems is we're not exactly sure what we're going to go and find, even if there are precursor missions. So I think one of the key design requirements is that either the vehicle system or the sensing system needs to be very flexible to be able to accommodate a large number of surfaces or other pieces that we're going to encounter there. I think that was one of the key unknowns we saw throughout everyone's presentation was, how do I know what I'm designing for, or do I design for the unknown?
One other thing, Jim.
Yeah.
I don't know if it fits here under vehicle systems or someplace else, but there's still a lot of open discussion about the type of capture mechanism, whether you're going to go grab regolith or whether you're going to pick off a rock or whether you're going to grab the whole thing, and if you are, how does that work with the dynamics? It's not part of the sensing system and algorithms, and it's not part of, so it could be under vehicle systems unless you want to bucket that somewhere else.
I think we bucketed it under alternate mission scenarios and concept of operations.
But I think a subset of that is just how you're going to actually grab whatever it is.
Oh yeah, that's true. That's true.
And actually, with that, there's a lot of discussion about precursors. I don't know if it goes there or alternative missions, but it seemed that was a.
Yeah, let's not lose that thought and see if we get there when we get to those. I think we do, but I'm not sure.
Especially on the capture system, but for all vehicle systems, being able to V&V it on the ground is incredibly important. And the capture system, the whole driving, philosophy underlying the reference capture system is the ability to V&V it on the ground. That's the overriding concern.
Okay.
Hey, Jim, one other input too, and I don't know if it goes here
Yeah.
or if you've got it. On vehicle systems, if the concept of designing for reusability, extensibility, long life, that I don't know if
we have a
you got a section on that?
extensibility category.
Okay, maybe that's where it goes.
And make sure when we get to that, if we haven't captured it adequately. Okay, anything else? Go ahead.
You brought up.
Would you go to a mic, please?
2 or 3 different presenters talked about using microsats as a probe. Is that under sensing or is that somewhere else? Because they really refer to them as sensors to know more about the target.
We had thought that like CubeSats and stuff, we were putting it under mission enhancements, if that makes sense.
Okay.
Anything else? And we'll go on to the next category. Sensing systems and algorithms. There's a wide range of sensor technologies discussed for various mission requirements, which includes characterization, rendezvous, proximity operations capture. Things to think about are the target size, shape, range, tumble dynamics, shape modeling, closed loop control with uncooperative target tracking, relative nav, rate matching, considerations for surface and subsurface characterization, crater detection tracking, asteroid structural strength, depending on your mission scenario. Candidate sensor technologies include visible IR camera, Lidar, laser altimeter, spectrometry, radar, tomography, and so on. We had discussions of integrated systems and algorithm development, and a lot of hardware and software adaptation from heritage systems, and we listed a bunch. So any comments? Tell the section that Heather wrote. Okay, we'll go on. Then the other topic areas that we had, and then we need to try to think about the different business strategies, one as well. But mission enhancements, what we put under there was robotic manipulators for enhanced asteroid characterization, dissimilar capture techniques, or an enabler for pick up a rock scenario. CubeSat class observation and sensor spacecraft, contact excursion probes, surface samplers, and I'm not sure it really kind of got talked about here, but taking advantage of about the 3-year transition to cislunar space to do further. So comments to this? Okay, that's pretty good. What's that? Yeah, when you wear everybody out, it's easier to get through these sort of things. But thank you for all the presenters.
I mean, we really want to make sure that we captured the mission enhancements that were in the paper.
Right.
So you don't see what you told us.
But we'll go on, and as need be, you know, you can contact me or us over the next day or two as well as we finalize this. Extensibility was our next major topic. Well, we talked about the similarity and needs of satellite servicing missions, potential for commercial applications, potential reuse as a cargo tug for translunar assets, planetary defense, asteroid deflection demonstration, space debris removal. I'm not sure everything actually got talked here today as much as we saw in some of the papers, but any comments to this section?
Can you list some examples of the potential commercial applications so we don't lose those thoughts?
That's a good idea. You want to ISRU?
Yeah, and then the fuel for satellites?
Fuel for satellites.
The maturation of the SEP helps geoconverge, right?
Maturation.
Whether it's PPU, quad junction cells, better deployables, the list goes on.
Spin-offs.
And I don't work for Boeing, Loral, or Lockheed.
Is it worth mentioning the robotic planetary? There is an extensibility. They're smaller, but it's
Robotic science mission? Sure. Okay.
I didn't see it here, but under extensibility, you know, if there are assets that are brought back, you know, it's not just human crewed missions from NASA that could go there. You know, other nations could go there. You know, there are, you know, industry could go there. In other words, there's clearly some interest in expanding the scope of what you do with the results.
Okay.
And there's also the trade space of, do you make this modular, which affects the extendability, or do you make it one piece and just duplicate that for another mission later?
Yes. Well, we tried to capture that in alternate mission scenarios or concept, really under concept of operations. Does that get at your point?
But you didn't really say anything about modularity anywhere.
Okay. Do you think it works okay as a concept of operations if we add, you know, into it?
It touched on testing it. It tests on extendability, lots of places.
Okay. All right.
Extending on the SEP comment earlier, you know, the SEP that we're trying to push here does an awful lot, not just for advancing the cause for geocom birds, but for doing things like deep space, space orbital debris, satellite servicing, human exploration, you know, deep space human exploration. I mean, that was one of our initial motivations for STMD doing these technology advancements in the first place, and I think we got to make sure we capture that.
Yes, some of those I thought that we were trying to capture with these.
Yeah,
words,
but
they're kind of
you
coarse.
don't. I guess what I would do is put under extensibility SEP specific.
Okay. Spell out
right?
SEP specifically.
Yeah,
Okay.
and because a lot of these are connected to SEP,
Right.
but you're not making the point.
Yep, I got it. I understand your point. Thank you.
Well, I guess if we're going to talk about those sorts of specifics, right, if we develop advanced robotics for this, those robotics with humans involved and work in conjunction with EVA, right, assembly of large observatories, assembly of a Mars excursion vehicle, right, anything involving the expansion of humans into the solar system with robotics and humans working together.
Okay. All right.
Just because when most people see satellite servicing, they think fixing things that are already existing there, as opposed to building new things that can't be built without it.
Okay. I see.
James mentioned that the leftover material would have value to industry. And it would have much more value to industry if it had some say in which rock was brought back. The any rock will do approach doesn't guarantee you really that you'll have an industrially useful resource. left over after the Orion mission.
Okay.
There was a point made earlier that you know, big rocks are easier to find than small rocks.
Yeah.
And that's of course because of the inverse square law. But what wasn't mentioned is that the slope of the population curve is minus 2.6, and therefore you actually find much more small objects than large objects. And furthermore, because of the fourth power radar law, they're much more likely to be in the radar, you know, within range of our radar systems, Arecibo and Goldstone. And so, if you go out just looking for these objects, they're overwhelmingly going to find the smaller objects, and you're going to be able to characterize the smaller objects preferentially to the larger objects.
Okay. I'm not sure yet how to capture that in this thought process, but we'll make a note. Okay, that would be very helpful. All right.
Oh, just one. I guess we didn't. It was only talked about briefly, but in terms of extensibility. You have a lot of capability up here, but you don't talk at all about any science capability. You could imagine using this in some fashion to do something really interesting in terms of bringing a telescope to L1 or L2 or something like that. There's a science potential here that I think you're not capturing.
With developing this kind of technology.
Yeah, if you want to move something very big to an interesting place, you have a possibility of doing that here.
Oh, okay. So it comes back to the SEP question especially, and it's not just for these sort of things, but even as a science potential. Moving things around.
Yeah, I mean, I don't know what that would be, but you know, we could be ambitious, right? So.
Okay, thank you. Yeah. Anything else in this category? Oh, yeah.
Yeah. So I have sort of a more general question. I'm wondering if it's within the scope of this summary to try and place some prioritization on this long list that has consensus of this group, or whether we're just trying to report on everything that was covered. I'm not sure if that is beyond what we're supposed to do.
My guess is we probably won't get there in the next 15 minutes. You know, it's a good thought, and maybe what we can do is, in terms of the findings, is one of the things you do is you take this list and start going through a prioritization activity. That may be how we could fit it in as part of our, you know, next steps. That kind of stuff is, we've got a lot of good ideas, but one of the next steps is to sort out which ones do we want.
Hey Jim.
Yeah.
I think the way that we should handle that, I mean, I don't disagree with it at all. I think we need to think about that. But I think that should be a discussion that we have with the wider group, sort of on Wednesday. We're all still here. That we could all say, well, what is the next step moving forward? I mean, we're not going to just take all this data and then send everybody away and say, okay, we're done, right? I mean, NASA's going to definitely interact with the participants here going forward, but we need to establish, you know, what we should do and how we should do it, and I think that's something that we should bring up as a topic for discussion with the broader audience. You know, we had some other panels that broke off here, as you know, apart from us here today in the parallel sessions, and I'm sure they brought up the same point.
Yeah. Okay, that's a good point. We'll figure out how to do that. Should we go on to alternate mission scenarios, concept of operations? We kind of had the various, you know, got introduced very quickly onto some of the options that were out there. The benefits of obtaining multiple samples from the RoboPal asteroid, mini-moons, good discussion on mini-moons and the alternatives there, and in terms of concept of operation, a separate transporter and capture vehicles, and trying to factor in modularity. Comments on this section?
So, as brought up earlier, the big one is, do we do precursors or not?
Precursors, yes. That
right,
needs to be on this list.
Or do you, you know, sort of a modification to that is, do you do a campaign where you go to more than one asteroid, you know, a small one and a big one, or some combination thereof?
Okay, that
or do you use your combination of assets to grab, you know, a combination of, you know, regolith and, you know, there's a whole different approach.
Okay.
Oh, I think you was.
Okay, so I'll expand on that one. So originally, when John did the Keck study, there was a longer period between launch and retrieving. They had a little more time, which opened up more targets and things like that. Then when we brought it into NASA, we focused on, you know, meeting certain milestones, doing it all ourselves without working with industry to fund it. So, you know, if you have these industry partnerships that we're talking about, where maybe they would fund a precursor, and maybe our particular return date wouldn't be 2023 or 2024. It might be a little bit out. It might open up a greater opportunity to leverage what James just said. Do we have a better campaign perspective? Can we partner with industry to make this better for all of us? And maybe get better targets.
And for that matter, industry or international.
Yes, yes.
Okay, go ahead.
Oh, okay. Just in terms of precursors, I want to expand this discussion a little bit. In that, I know everyone's talking about the tight timing and the rest, but really one of the most important precursors you could do is do a survey that looks for near-Earth objects, right? So then you can span the number of objects we had, and then you have many more options. You don't know what options we have right now. Right now we have very, very few options in terms of mission targets and the rest, and I think that could be the showstopper, right? So you want to avoid the showstoppers. So that's something I think NASA strongly has to consider, is some kind of space-based NEO survey.
So listening to the talks, I sensed a lot of interest in resources and ISRU as a driver, and perhaps that's a way of answering the why. And so a lot of commercial interest on what do you do with the asteroid and what is its ultimate purpose. And I think ISRU should be captured as a potential driver for this mission.
Okay.
I have one comment under extensibility. If we, for example, pick up a rock from a larger rock, there's the question of should we leave something behind on the rock, the big rock that we took the little rock from, a beacon or some other item.
Okay.
Okay.
Okay, thank you. Anything else? The other category that was suggested that in addition to these 5 was different business strategies. Anyone want to comment to that, or otherwise we'll take a cut at. Okay. Thank you. That went very well. That really was very helpful. Now this one's the harder one. We did the easy one, and this one we struggled with ourselves too. So even more than summarizing what was in the papers is what are our findings relative to this initiative planning, and honestly, like I said, this area in particular, we didn't have quite the guidance that we do now. So, but anyways, I'll just talk through it, and things that we would think would be next steps is I think what this is really more worded around. Establish a concise set of mission objectives and figures of merit that includes extensibility, commercialization considerations. Perform an assessment of the various mission concept options against these FOMs, including weighing technology approach and mission enhancement options in doing so. Focus the risk reduction activities consistent with the mission concept approach and leveraging the inputs. And consider a follow-on ARM workshop for sensor technologies that would address the potential for integrated sensing system that is able to support all mission phases and broader NASA exploration needs. And like I say, we really, this was a much more difficult thing for us to do when we were talking it, but this is what we have right now. We'll open the floor for thoughts.
Just one comment. The top one would address the cost versus objectives issue. Some of the launch vehicle issues, one of the launch options could take the entire budget and have nothing to launch. So that would be very helpful to understand how much is actually being allocated and thought of.
Okay. Anything else?
Just looking at this list, one thing I think which could be done, or I think I'll put it a different way, which should be done, is more incorporation of the small body science community into all these discussions. For some reason, they're not being included in any great degree or not being invited, and yet they have almost all the expertise that exists on these objects. So I think we need to have NASA-sponsored workshops to discuss these things.
Okay, good. Thank you.
Well, until I heard Deep Space Industries talk, I would have argued against more is better. But if you guys are going to make fuel out of it, maybe more is better. And we are in America anyway. That is our general approach to everything. But is enough enough? I mean, if a figure of merit is going to be how much mass we bring back, that may drive a lot of decisions. Then is 1 ton enough? If 1 ton is enough, that may mean we spend our money elsewhere in the system rather than, are these guys going to build a 15-meter bag or a 10-meter bag if we fly a bag? Right? So is more always better? If it ends up killing the mission because we get ground into the ground on being able to get that much, then maybe we could pick a number that was reasonable and that it just isn't. All right, that's enough.
I think the top figure of merit should be, can you sustain this activity? Doing it once is not very interesting. So that should be the figure of merit. Is it, can you continue doing it? That would argue that the more comes in the continuation and the repeatability rather in the size of the initial mission.
Well, then we're talking about transferring of the technology to private industry who wants to do it again and again, because other than the scientists coming back arguing that we need to do it again, I think this community's only signed up for one.
Right.
But I don't speak for
Do you want to spend that
headquarters.
much money to do it
Go
once?
ahead. Please do.
Well, but it's not just that. We're spending the money to do lots of other things. Develop the technology, practice EVAs to longer distances, et cetera, et cetera. So it's not just spending all the money for 1 ton. It's for all the other things in addition. So as long as we can transfer the technology to you, does that satisfy the continual stream of getting more and more of the rocks back?
What you decide to develop, if it's only done according to your figures of merit, because you're the only one making decisions about the system, means that the technology that gets developed may not be applicable or useful to the private sector. So that's why a COTS-like approach, where NASA said we want this many tons delivered to the space station. What else you do with the Dragon system is up to you.
Well, if you're going to sell it back to us, that's a different story, right? If you're going to sell it back to us, now we help ourselves by bringing more to cislunar space.
Mark, did you want to add something?
Well, I was just going to try to help. Heather turned around and cued me. There's more than one aspect to extensibility. There's extensibility of using the asteroid more per industry things. There's extensibility of using the technology. But there's also extensibility that Steve Stitch will talk about in the crew session tomorrow of using these technologies and systems to accomplish missions beyond this. Lunar missions, Mars missions, other things. So the broader NASA team that is working this is looking at it from multiple points of view. So
to be fair, this session is on the redirect.
Correct.
Right?
Yes. So that's
the point. When we talk about extensibility, we're talking about extensibility of those elements.
correct. And that's actually, James is right. That's exactly what I was going to say, is in this session, you focus on those asteroid pieces, but in other sessions, the broader NASA team is considering other aspects.
Although the selection of material might hinder or help the future missions. So there is some downstream.
You want me to repeat that?
And
So I'll
as you
repeat that.
address your figures of merit, you want to look at, is there a potential follow-on use to
Yeah.
this? Does someone pick up this technology and make it available to us 10 years later when we next need it? Or if it gets shut down and forgotten immediately because we only did it once, we develop a lot of technology that doesn't help us follow on. So having that transition into the commercial sector, I mean, we're doing that right now on the science side. We've been building a lot of technology for the last 10 years. And if we can't get it to the commercial industry to sustain it, we can't sustain it anymore. So we're abandoning technology that we've been building for a while because we haven't thought through the what's next and didn't have a way to hand it off.
There's two points that I guess I was going to bring up. An example of why you need to actually have some discussion along this line of technology is even within sub-technologies, SEP technologies. And let's say that we all agree that, well, we're probably going to go down the Hall thruster route just because that's the most mature and that we could bring online to do this kind of mission in this time frame. Even if you got consensus about that, which you wouldn't, the fact of the matter is if the ARM mission as currently outlined by the on the reference team goes with 12.5 kilowatt individual thrusters, the geocom community would say those are useless for our needs. They don't want that large a thruster. So transferring technology is very dependent on what the rest of the community wants. And we need to make a point that that has to be discussed and acknowledged in some way. So that's the first point that I wanted to make, and I think we should try to capture it within this type of discussion that you're bringing up on findings. The second goes back to how we're dealing with the business case, because the entire discussion that you just heard, COTS versus, well, if the government goes and does this as a one-off and then sends, and then, says, okay, now we could hand off the technologies to be sold back to us. That's a completely different mindset of how we should go about this. And I think that there's going to be very big differences in how partnerships occur given different scenarios on the business case.
Okay. It is 5:30, so we've reached the end of our session, but is there any other comments you want to make on this? Okay, any last comments for the session? Hopefully everybody enjoyed it as much as I did. Well, I want to thank everyone and thank my colleagues for participation today. It's really an excellent session. I very much appreciate it. Thank you.
Thank you.
Oh, and we'll do our best to capture the essence of what we've been talking about, but odds are we won't get it quite right. We're all. Is that right?
Coming up. Yeah.